We have to have some laws in the country about how the biometric data will be used, how it will be stored, how it will be safeguarded, and does the user have a consent to provide that data? Of course, if you are in the public domain, if there are surveillance cameras and you are walking on the street, the government has a right to capture your face because you are in a public place and they want to maintain the security and they want to detect if any crime is being committed and who was in the neighborhood of a criminal activity, things like that. Okay, but even the government should not share that data with anybody. So since I'm more familiar with the India's Aadhaar program, there is an act of parliament when Aadhaar was passed. Okay, under that law, when Aadhaar collects the data, biometric data for national ID, it cannot be shared with any other government agency. The police cannot have access to it. The immigration agency cannot have access to it. It is only for the purpose of social benefit. It's a very powerful law which preserves the privacy. That is, when I'm providing my biometric data to get an Aadhaar card, it cannot be used, it cannot be shared with the police. And if somebody shares it, it is under the penalty of law. Okay. In fact, when an authentication query goes to the Aadhaar server in India, the only answer which comes back to the merchant is yes or no, whether this 12-digit ID is linked to that fingerprint or not. That's all. No biometric data ever leaves the Aadhaar server. It's only a one-way transfer. During enrollment, the biometric data goes to the Aadhaar server. After that, it never leaves.
Okay, thank you very much, Professor Jain. We have learned a lot of your topics from your presentations. Okay, to close these sessions, let us give applause to Professor Anil K. Jain.
Thank you.
Yeah.
Thank you so much, Professor Jain. It was really very
Ya, baik, terima kasih Dr. Anto tadi yang sudah menyampaikan keynote session yang pertama begitu ya dengan Biometric Recognition bersama dengan Prof. Anil K. Jain begitu. Nah, yang kedua, keynote session yang selanjutnya kita akan langsung di moderatori ya. Kebetulan sudah bersama dengan saya pada pagi hari ini Dr. Hary Budiarto. Nah, sebelumnya saya akan membacakan terlebih dahulu untuk CV-nya ya dari Dr. Hary Budiarto. Tapi Teknopren yang pasti jangan kemana-mana seperti yang sudah saya sampaikan tadi ya, bahwa kita hari ini akan ada 9 session dan sudah ada 1 session tadi yang pertama dengan Prof. Anil dan masih ada 8 session termasuk yang setelah ini akan dimoderatori langsung oleh Dr. Hary Budiarto. Dr. Hary ini adalah lulusan ya untuk S2-nya dari Faculty of Computer and Science Universitas Indonesia Jakarta ya, lulus tahun 99. Kemudian di tahun 99 sampai dengan 2004 langsung melanjutkan S3-nya mengambil doctoral degree ya, Department of Electrical and Electronics Engineering di Tokyo Institute of Technology ya, pastinya di Jepang begitu. Dan sekarang Dr. Hary ini ya bergabung bersama dengan BPPT ya sebagai perekayasa ahli utama atau Principal Engineering ya di Pusat Pelayanan Teknologi Tenaga Ahli Kerja BPPT bidang TIK ya untuk saat ini. Langsung saja kita akan menyapa Dr. Hary. Selamat pagi.
Selamat pagi Mbak Rara
Ya, sehat dok?
Sehat.
Dari kemarin kita sudah memulai dan masih ada sampai hari Jumat, tetap semangat ya?
Semangat.
Yes, dan hari ini Dr. Hary akan memoderatori Joy Huang ya. Akan selanjutnya diperkenalkan oleh Dr. Hary. Baik, kalau begitu langsung saja saya serahkan kepada Pak Hary, silakan.
Thank you very much, Miss Rara. Good morning, Mr. Huang. How are you?
Good morning. Good morning. It's good.
Assalamualaikum warahmatullahi wabarakatuh. Para peserta webinar pada pagi hari ini, selamat pagi, salam sejahtera, Om Swastiastu, Namo Buddhaya, salam kebajikan, salam sehat untuk kita semuanya. In this session, we will continue with presentation from Mr. Joy Huang. The title of the presentation is Building All Scenario Intelligence with Intelligent Twin. For the participant of the webinar, that 40 minutes will be used for presentation only. If you have question, please write in the QA. Huawei team will answer all your question. Question can written by Indonesian and in English. Ya. Bapak Ibu peserta webinar yang kami muliakan, ya, bahwa pada hari ini untuk session yang kedua, ini 40 menit akan kita gunakan untuk presentasi saja oleh Mr. Joy Huang. Dan ini akan ada presentasi dan video, maka pertanyaan ini silakan dituliskan di bagian QA dan nanti akan dijawab oleh tim Huawei. Now I would like to read a biography of Mr. Huang. Mr. Joy Huang is the Vice President, Cloud and AI Strategy. He is responsible for product management and industry solution planning, covering data center, cloud, artificial intelligence, and big data. Mr. Huang has worked in the ICT field at Huawei for nearly 22 years. He was the Vice President of Huawei Silicon Valley, R&D Center in the United States, and has extensive experience in product management, solution planning, and research. Mr. Huang has participated in many global ICT projects and worked closely with the key regional customers in China, Europe, and North America to provide innovation solutions. Mr. Huang graduated from Guangzhou University of Science and Technology in 1997. With a master degree. Please, Mr. Huang, to start the presentation.
Good morning. Thanks very much for invitation of organizing committee of this summit. I'm honored to give this speech on behalf of Huawei. Today, my topic is building all scenario intelligence with intelligent twins. So next page, please. So next page, please. Yes. So I will talk about three parts. First is industry trend. Second, I will introduce several practices of various industry. Third, we'll talk about in Indonesia, for Indonesia. And today, the intelligent world at your fingertips is moving towards every ordinary person, every enterprise, and every industry. And our global industry vision predicts that 97% of large enterprises will adopt AI by 2025. So AI technologies will be the key to digital transformation, from supporting system to core production system, and the main business process, effectively improving enterprise productivity, creativity, and competitiveness, and creating huge new business values. So next, please. Next page, please. So previous one. AI works with cloud, 5G, and edge computing. So multiple technology convergence will accelerate the adoption of AI. All these technologies bring new experiences like smart home, V2X, promote new applications like cloud VR, creating new industries like smart media, smart transportation. Next. With the rapid development of AI, so we clearly see that the various industry applications have gradually integrated into our daily lives and are entering new core businesses of various industries. So around 600 AI-related projects in more than 10 industries. We find out that 30% of enterprises have already adopted AI into their systems. Once AI is deployed in enterprise core system, it can create great value, increasing profit by 18% on average, according to our statistics. So the very important thing is how to select the top scenario in every process. This is very important. So next. So we learn from all the cases. So how to help enterprise better adopt AI? It's not only single point of technology. We should think about the whole IT architecture point of view. So intelligent twins is a system reference architecture for the intelligent upgrade of IT architecture. For digital transformation, we think a very important new step is intelligent upgrade. So it is an integrated intelligence system with collaboration across cloud, network, edge, and device. It has 4 layers, we think. Intelligent interaction. So this layer is like the arms and the legs of intelligent twins. It connects the physical and the digital world, allowing software data and AI algorithms to flow freely across cloud, edge, and device. It collects all the data from the physical world. And at the same time, it can control, after you centralize all the data and empowered by AI, it can control the physical world experience. So intelligent interaction layer is very important. The second layer is intelligent connection. This layer is like the body of intelligent twins. It helps the intelligent twins to cover all the scenarios and connect all the things. The intelligent hub, this layer is the brain and the decision-making system of the intelligent twins. It is built on cloud infrastructure and empowered by data and AI technology. And intelligent applications, this layer is the best showcase of the value of the intelligent twins. So we innovate together with customers and partner ecosystem to combine ICT technology with industry know-how, industry expertise. So therefore, we can improve the user experience, optimize process, and enable the new innovations. Next, please. So intelligent twin is not only a data-driven, because we think for AI, data-driven is not enough. We also need to think about knowledge-driven. So in intelligent twins, we launched the industry first full life cycle knowledge computing platform, combine AI with industry know-how to better support the intelligent innovation of various industries. Take China National Petroleum Corporation as an example. With the help of AI, CNPC quickly built a professional oil well logging model, implementing intelligent identification of oil and gas layer, shortening the evaluation time by over 70%. Next, please. So next page, please. So we will move to the second part. Let me show several industry cases of intelligent twins. First, we have launched the city intelligent twins with Shenzhen and some other cities in China as well. So city intelligent twins can realize the city's all-domain perception, network-wide collaboration, full-service convergence, and all scenarios intelligence. The city can sense, the city can think, and the city can evolve, and providing proactive, precise, and intelligent services to citizens and enterprises. For example, in Shenzhen, 98 of the administrative approval items are handled online, and the traffic efficiency during the peak hour is improved by 10%. The airport departure average waiting time of passenger is shortened by nearly 40%. So next, please watch the video of Shenzhen Intelligent Twins. Please play the video.
This is a novel city. She embraces new ideas and endeavors. From a special economic zone to a digitally inspired city, technology is reshaping every aspect of life here. Monitor waterlogging and sewage for a cleaner, greener Shenzhen. Precision weather prediction safeguards every trip. Drone-powered electrical grid inspections keep every household warm at night. Rapidly respond to flight schedule changes for a more efficient airport. AI-powered ports make logistics faster and safer. High computing power applied to finance spots potential risks lurking in data fluctuation. Monitor every intersection and traffic light to optimize traffic flow. Autonomously evolving AI technology diagnoses massive numbers of patients in seconds. Intelligent image analysis makes the city safer. The Intelligent Operations Center coordinates city-wide operations and real-time scheduling with just a click. The synergy of 5G, cloud, AI, and computing creates a perceptive, conscious, evolvable, and familiar city.
So next, please.
This is a novel city. She embraces new ideas and endeavors from a special...
So next page, please. Thank you. So in the field of transportation, so AI can improve the efficiency of the transportation system. So the radar, camera, and edge computing system are used to replace manual toll collection. So vehicles and the plates can recognize by AI so that highway traffic efficiency can be greatly improved. So vehicles can be tracked to avoid fare evasion. Besides, by creating real-time road monitoring maps, AI helps people implement road condition identification and the vehicle-road collaboration, providing a basis for assisted driving and autonomous driving. So intelligent twins improves traffic efficiency, reduce congestion, and energy consumption. So make the free flow come true. Next, please. And in the field of airport, AI helps improve airport operation efficiency by analyzing all the data, including aircraft stand, flight status, and historic operation data. AI technology can realize smart aircraft stand allocation. By using AI, the bridge match rate is increased by 5% and the conflict rate is reduced by 10%, compared with manual scheduling. For airports with annual passenger volume around 50 million. So 2.5 million passengers do not need to take shuttle bus every year. So next page, please. So in the scientific research field, so AI computing cluster is becoming a trend. So last year, we released the world's fastest AI training cluster, Atlas 900. It has been deployed in Shenzhen Pengcheng Laboratory. So with the computing power of 256 pflops to 1,024 pflops, Atlas 900 completes widely used image classification model, ResNet 50 training in just 59 seconds. So this year, we optimize the software tuning. We reduce the training time to 28 seconds. So continuing to lead the world records. So Atlas 900 with only 16 racks can provide the same computing power like a x86 server with 6,195 racks. At the same time, the power consumption is only 1/50. It can be widely used in scientific research and technological innovation. So next page, please. In the field of healthcare, so as you know, AI helps people fight against the COVID-19. So AI technologies make virus detection faster, and AI-assisted diagnosis can complete COVID-19 scan analysis in just seconds. And AI makes drug discovery more efficient, from months to just hours. And AI healthcare service on Huawei Cloud have been serving hundreds of hospitals worldwide. So next, please.
We use an extremely accurate AI-powered selection process to identify the best chilies quickly and efficiently.
So in this case, you can say AI technology is used to quickly and accurately identify the quality of chili, improving the efficiency and quality of chili production. Can you go to previous page? There one more case for food industry. Can you go to previous page? Can you go to previous page? Yes. So in the field of food and retail, as you can see this case, this is an AI company in Singapore developed a fruit recognition system by using our AI platform. It not only can distinguish apples from orange, but also between apples, such as Envy, Gala, Fuji apples, and automatically calculates the price. And AI makes supermarkets smarter. Okay, please move to next.
We use an extremely accurate AI.
Yes. In the power industry, AI enables intelligent grade inspection, replacing manual inspection. So the video on the left shows the traditional manual inspection mode. So in this mode, engineers must climb high pole towers to inspect high voltage lines step by step. This is not only dangerous, but also not efficient. So with AI, which shown in the video on the right side, AI inspection leverages cameras and drones that are embedded with AI hardware and edge computing to implement automatic inspection. The new AI inspection solution can shorten the inspection time from 20 days to just 2 hours, improving the efficiency by 20 times. So next, please. So in the field of manufacturing, AI is also helping a lot. So workers can implement quality control, efficiency control, and precise scheduling. So intelligent edge computing enables real-time device interconnection, data sharing, and collaborative operation, implementing intelligent detection, improving the yield rate, and achieving stable production. Next, please. So next page, yeah. So for the society, AI can do good to Earth and environment protection. So please play the video.
When I first came to the rainforest in Central America, one creature above all stood out, the spider monkey. This monkey helps with seed dispersal, and their presence is essential to the overall health and biodiversity of the whole rainforest. We can better protect the spider monkeys if we listen closely and better understand nature's symphony. Upcycled Huawei phones act as the ears of the ecosystem. These phones call into the cloud every second of the day and night in the pouring rain, blistering sun, and dripping humidity. The way our technology is built actually involves these guardians, which are old smartphones in boxes up in trees, capturing all the audio of the forest, streaming it up into the cloud, and then in the cloud we analyze for different things. It's not just about detecting chainsaws anymore, vehicles and the rest. It's about understanding the fabric of nature, ecology of the forest, just through sound. The rainforest sounds are often too complex for humans to interpret, but technology can hear the many complex details of this symphony.
AI makes it possible. At the moment I'm collecting 200,000 hours of data, so without AI we can't physically analyse these large data sets.
The more we know about them, the easier it is to protect them, and the easier it is for us to show the world that they matter. And that is part of our mission as well.
Okay, next. So let's talk about in Indonesia, for Indonesia. So next, please. So next page, please. So in fact, we are very pleased to see that Indonesia government's vision is to build Indonesia into a developed country and become one of the world's top 5 economies by 2045. In addition, the government has set AI as a national strategy this year, aiming to promote industry upgrade, improve the digital economy, and promote national development through AI. 6 areas will be prioritized under the AI strategy framework. So how can we promote the development of the AI industry? So we believe 3 core pillars are important. So digital infrastructure and digital industry ecosystem and the talent. The first, digital infrastructure. So AI requires collaboration of multiple new technologies, as we discussed before, such as cloud, big data, IoT, 5G, and blockchain. Second, so digital industry ecosystem. So we need to continuously develop more AI industry partners, developers, and application vendors. The third thing is talent. So AI education and the talent development are important factors. So next page, please. On the 20th of last month, we signed an MOU with BPPT and to work together to develop Indonesia's digital economy. The two parties cooperate in new technologies such as AI, cloud, and 5G to jointly promote the development of the industry ecosystem. So we will also help Indonesia develop local talent and achieve sustainable development by sharing and transferring knowledge and technology. Next, please. So during 20 years at Huawei Indonesia, so we have been working hard to provide a better digital infrastructure for the local country and build a better Indonesia. During this year's epidemic, we provide large capacity microwave technologies to help Sabaru, Ireland, achieve high-speed connection coverage. And in the Paramedica Hospital, we provide better Wi-Fi 6 connections and the CT scanning solution based on cloud and AI, and provide a video conference system to help the hospital better communicate with the outside world. We also partner with Tachi to build an e-learning platform that provides students with an online education platform that will help them learn new knowledge during the epidemic. Next page, please. Next page, please. Next page. So in addition to applying new technologies, we also participate in the cultivation of local ICT talent. Previous page, please. So we have an ICT talent development program by 2025. We hope to help Indonesia develop 100,000 ICT talent and build a better talent base. The form of talent development include technical training and certification. So ICT competition academies, vacation training camps, and a visit to Huawei headquarters, the related technology field, including cloud, AI, 5G. And so far we have benefited 12,000 engineers and over 7,000 students. So we will also discuss with the Indonesia government about the quick win and the implementation plan of the AI industry and build AI computing center to enable AI industry development and technology applications. We hope to build an AI computing center to support the development of our 4 platforms, thereby enabling the AI technology to help the industry to upgrade. First is Common Computing Service Platform, provide inclusive public computing service for local enterprise through government policies. Second is Application Innovation and Incubation Platform, provide inclusive public computing service for local enterprise through government policy. The third thing is Industry Aggregation Development Platform, build an ecosystem innovation center, drive the centralized and intensive development of AI industry. The first platform is Scientific Research Innovation and Talent Development Platform, support scientific research, innovation, and AI talent cultivation, achieve breakthroughs in common AI technologies. We hope to promote the AI industry development and implementation by the construction of AI computing platform, of AI computing center plus 4 platforms. Next, please. So in Indonesia, for Indonesia, Huawei will continue to invest in Indonesia. We have signed MOU with BPPT, and we'll also sign MOU with IRPI as a scientific research institute to cooperate in the field of scientific research and innovation. In addition, we cooperate with many universities to hold various forms such as AI bootcamp, ICT computation, training courses, and AI courses to cultivate the next generation of talent. Huawei will work with government agencies, research institute, and industry partners to promote the development of Indonesia's digital economy and upgrade the industry. Next, please. To make a summary, AI is booming and can be applied into many industry scenarios. So intelligent twins could be a best reference architecture for advanced intelligence. So we would like to cooperate with the government, enterprise, and partners in Indonesia to take the lead in adopting AI, building core competence with intelligent twins. Thank you. That's all of my presentation.
Thank you for presentation, Mr. Joy Huang. It was very interesting presentation on intelligent twin, and Huawei has done a lot of cooperation with various institutions in Indonesia. We have 10 minutes for question. Maybe only one question. Do you want to answer, Mr. Joy Huang?
Yes.
Okay, I read the question. In order to build the intelligent twin, we have to provide the stable connectivity. As we know that Indonesia is still facing several issues related with connectivity. In your opinion, how far Indonesia readiness to adopt this technology?
Okay, I think it's a very good question because I think intelligent twins is a very good reference architecture. So when we talk about all the intelligent connections, we also need to think about the real scenario when we deploy it. So this is why I think the edge computing is very important. And we talk about the layer, the intelligent interaction layer. So this layer is very important because the AI cannot be only in the central place. AI should be at the edge, in the device as well. So if we can distribute the AI capability, then even sometimes the connection is not good enough. So the edge computing still can perform all the AI capabilities for the inference. So we use the central place to collect data and do the training, but the edge and the device can do the inference. So therefore, sometimes if we design right, so we can make sure no impact to the real-time system, but we can do the training offline when we have better connections. So I hope I can answer part of this question.
Thank you for your answer. Bapak Ibu yang saya hormati, masih banyak pertanyaannya, nanti akan dijawab oleh tim dari Huawei. Sorry, Mr. Huang, I am summarizing your presentation in bahasa.
Okay, thank you.
Bapak Ibu, peserta webinar, bahwa saat ini industri sedang bertransformasi dari go cloud. Jadi yang era yang lalu adalah cloud, sekarang menjadi era intelligent. Jadi kita go intelligent. Inovasi di bidang kecerdasan artifisial ini tidak lagi terbatas pada satu skenario tunggal. Nah, jadi Mr. Huang menawarkan ya, tren yang berlaku sekarang ini, bagaimana kecerdasan artifisial ini mampu untuk mengantisipasi semua skenario. Kemudian intelligent twin ini mendayagunakan cloud sebagai fondasi dan kecerdasan artifisialnya ini sebagai intinya. Melalui kolaborasi di seluruh cloud, jaringan dan edge dan perangkat, akhirnya intelligent twin ini bisa memungkinkan sistem terbuka yang cerdas, mampu melakukan persepsi untuk semua dimensi, kemudian bisa berkolaborasi untuk semua domain, penilaiannya sangat tepat dan berevolusi berkelanjutan, serta mampu memberikan pengalaman yang cerdas bagi masyarakat, kemudian tata kelola kota, serta beberapa perusahaan bisa melakukan untuk semua skenario. Jadi itu ringkasan dari teknologi intelligent twin yang dipresentasikan oleh Mr. Huang. Sesuai dengan kesepakatan, tim Huawei akan menjawab semua pertanyaan dalam QA, dan ini cukup banyak pertanyaannya. Jadi para peserta webinar tidak usah khawatir. Kita akhiri presentasi Mr. Huang pada sesi ini. Mr. Huang, thank you very much your presentation, very interesting, dan this important for technology intelligent twin. For the end of the session, let me give applause for Mr. Joy Huang from Huawei. Thank you very much.
Thank you.
Saya kembalikan lagi ke pembawa acara. Silakan Mbak Rara.
Baik, terima kasih Teknopren yang masih setia bergabung dengan kami di Inovasi Indonesia Artificial Intelligence Summit 2020 untuk hari yang kedua, ya, setelah kemarin hari pertama pembukaan, dan tadi sudah ada 2 keynote session. Dan yang baru saja bersama dengan Dr. Hary Budiarto M.Kom adalah Joy Huang, Vice President of Huawei Cloud and AI BG. Pak Hary, gimana Pak tadi tentang presentasi keynote speech mengenai building all scenario intelligence with intelligent twins? Gimana Pak?
Jadi tadi sudah ada 2 sesi ya Mbak.
Betul.
Jadi yang pertama kita bahas tentang science, ya, tentang bagaimana algoritma untuk AI biometrik. Dan selanjutnya adalah kita masuk ke real aplikasi untuk AI yang tadi barusan dipresentasikan oleh Mr. Huang. Jadi para peserta webinar ini bisa melihat bagaimana sih manfaat AI untuk kehidupan. Nah, nanti selanjutnya akan banyak lagi, ya, banyak lagi bagaimana kita mengembangkan dan memanfaatkan. Jadi ada ilmu dasarnya, ada teorinya. kemudian kita juga melihat aplikasinya seperti apa, demikian juga industrinya seperti apa, agar hasil riset dan inovasi ini bisa langsung bisa dimanfaatkan oleh masyarakat.
Amin. Mudah-mudahan bermanfaat ya tadi keynote session yang sudah disaksikan bersama. Pak, satu lagi Pak, terakhir bocoran, boleh nggak? Apa sih keynote session yang dinanti-nantikan sama Pak Hary, pengen banget untuk mengikuti nanti?
Ada yang menarik ini. Setelah ini adalah Yann ya.
Yann ya, dari Facebook.
Ya, dari Facebook. Para peserta webinar kan banyak sekali menggunakan Facebook.
Betul, termasuk Pak Hary.
Ya, banyak sekali.
Oke, baik. Jadi setelah ini akan sangat menarik sekali keynote session-nya ya, Pak Hary. Baik, terima kasih Pak Hary untuk waktunya menjadi moderator kita pada kesempatan kali ini. Dan jangan kemana-mana dulu Teknopren, karena nanti kita akan bergabung dengan Prof. Dr. Bambang Riyanto Trilaksono yang akan langsung membawakan keynote session yang ketiga dengan topiknya Self-Supervised Learning and the Future of Machine and Deep Learning, tentu saja yang ditunggu-tunggu juga oleh Pak Hary ya, dari Profesor Yann LeCun, VP and Chief AI Scientist Facebook. Jangan kemana-mana Teknopren. Ya, terima kasih Tenopren masih bergabung bersama kami di rangkaian acara Inovasi Indonesia Artificial Intelligence Summit 2020, di mana hari ini kita akan mendengarkan ya, sudah ada 2 keynote sessions dan masih ada lagi sisanya, ada 7 ya keynote sessions berikutnya. Nah, ini yang ditunggu-tunggu juga oleh tadi Dr. Hary begitu ya, yang juga ditunggu-tunggu pastinya oleh Teknopren semuanya. Dari Facebook akan turut tampil di keynote session kita pada pagi hari ini, yaitu Profesor Yann LeCun, VP and Chief AI Scientist of Facebook ya. Dan moderator pada pagi hari ini adalah Profesor Dr. Bambang Riyanto Trilaksono dengan topiknya Self-Supervised Learning and the Future of Machine and Deep Learning. Saya sebelum ke Prof. Bambang begitu ya, saya akan bacakan CV dari Prof. Bambang. Prof. Bambang Riyanto Trilaksono ini ya, in English ya, was born in Banyuwangi, Indonesia on November 15, 1962. He received bachelor degree in electrical engineering from Bandung Institute of Technology, Indonesia in 1986 ya. He received master and also doctorate degrees in electrical engineering from Waseda University, Japan in 1991 and 1994, respectively. Currently, he is professor at School of Electrical Engineering and Informatics, Bandung Institute of Technology atau ITB ya. His research interests are artificial intelligence, robotics, and control. He is also a research fellow at University of New South Wales, Australia, and serves as the editorial board member for several journals, including International Journal of Intelligent Unmanned System, International Journal of Unmanned System Studies, Journal of ICT Research and Applications. He also received several awards, including Torrey Science and Technology Award in 2004. He is the director of Advanced Robotics Lab in ITB. He serves as scientific advisor of the Center for Artificial Intelligence in ITB. He was vice rector for research, innovation, and partnership in ITB, of course, in 2015 until 2019. And also he is a member of Indonesian Academy of Sciences. He is co-founder of a number of startups, and one of which is AI startup Reset.ai. Oke, langsung saja. Panjang sekali ya CV-nya, luar biasa. Prof. Bambang ini pasti memang seorang praktisi AI begitu ya, dan pasti akan sangat menarik sekali perbincangan kita pada pagi hari ini. Saya langsung menyapa saja Prof. Bambang. Prof, selamat pagi.
Selamat pagi Bapak Ibu sekalian.
Iya, selamat pagi Prof. Bambang. Mungkin bisa ditampilkan wajahnya di sini.
Selamat pagi.
Iya, Prof, sehat Prof? Nah, ini sudah muncul ya. Sehat Prof?
Alhamdulillah, Mak. Alhamdulillah.
Baik.
Sehat.
Ini di Bandung ya Prof ya?
Benar, Mbak.
Sedang di kampus atau dari rumah ini?
Di rumah.
Oh, di
WFH,
rumah.
di rumah.
WFH ya, baik Prof. Kita akan langsung handover ke Prof. Bambang untuk membawakan keynote session kita yang ketiga pada hari ini, Self-Supervised Learning and the Future of Machine and Deep Learning. Sudah siap, Prof?
Siap, sambil menunggu Profesor Yann LeCun untuk join ke meeting kita.
Kita akan mungkin Prof nanti bisa membacakan terlebih dahulu CV-nya.
Baik.
Ya,
good morning, everyone. It is my great honor to chair this session with Professor Yann LeCun as the keynote speaker. Professor LeCun will be delivering a talk on self-supervised learning and the future of machine and deep learning. I hope this topic is of interest to many of you. And before starting the presentation, let me introduce Professor Yann LeCun.
Prof
Yann
Bambang,
LeCun is...
bentar, boleh?
Yes.
Agak mundur sedikit, Prof, agar nampak jangan jelas wajahnya.
Oh baik.
Iya.
Baik, terima kasih.
Iya, mantap sekali. Silakan dilanjutkan, Prof.
Okay, let me introduce Professor Yann LeCun. Yann LeCun is a VP and Chief AI Scientist at Facebook and Silver Professor at NYU, affiliated with the current institute, the Center for Data Science and the Center for Neuroscience and the Electrical and Computer Engineering Department. He was the founding director of Facebook AI Research and of the NYU Center for Data Science. He received the Electrical Engineering Diploma from IEE Paris in 1983 and a Ph.D. in Computer Science from Sorbonne University in 1987. After a postdoc at the University of Toronto, he joined AT&T Bell Laboratories in 1988 and later becoming the head of the Image Processing Research Department at AT&T Labs Research in 1996. He joined NYU as a professor in 2003, following a brief period at the NEC Research Institute in Princeton. In 2012, he became the founding director of NYU Center for Data Science. And in late 2013, he was named director of AI research at Facebook, remaining on the NYU faculty part-time. He held a visiting professor chair at Collège de France in 2015 and 2016. His current research interests include AI, machine learning, computer perception, robotics, and computational neuroscience. He is best known for his contribution to deep learning and neural networks, particularly convolutional neural networks model, which is very widely used in computer vision and speech recognition application. He has published over 190 papers on these topics, as well as on handwriting recognition, image compression, and dedicated hardware for AI. LeCun is a founder and general co-chair of ICLR and has served on several editorial board and conference organizing committees. He is co-chair of the program Learning in Machines and Brains of the Canadian Institute for Advanced Research. He has been on the Science Advisory Board of IPAM since 2008 and the Board of Trustees of ICIRM. He has advised many companies and co-founded startups named Elements Incorporation and Museami. He is the New Jersey Inventor Hall of Fame. He is a member of U.S. National Academy of Engineering, a Chevalier de Legion d'Honneur, a Fellow of AAAI, and the recipient of 2014 IEEE Neural Network Pioneer Award. The 2015 IEEE PMI Distinguished Researcher Award, the 2016 Lofi Lifetime Achievement Award, the 2018 University of Pennsylvania Bender Award, and the honorary doctorates from IPN Mexico and EPFL. He is the recipient of the 2018 ACM Turing Award with Geoffrey Hinton and Joshua Bengio for conceptual and engineering breakthrough that have made neural networks a critical components of computing. LeCun, together with Hinton and Bengio, are referred to by some as the godfathers of AI and the godfathers of deep learning. What outstanding CV of Professor Yann LeCun. Okay, let me check if Professor Yann LeCun already joining this meeting. Professor Yann LeCun, are you already joining this meeting?
Kelihatannya belum ada, Pak Bambang.
Oh, belum ada.
Iya, saya lihat di partisipan listnya belum ada.
Oke, baik, Pak.
Baik.
Saya kembalikan ke MC.
Baik, Prof. Bambang Riyanto Trilaksono. Ini hari ini dengan Prof. Yann LeCun, ya, selaku VP and Chief AI Scientist Facebook. Ini akan membahas mengenai apa nih? Mungkin teknoprend nih yang sedang menunggu, boleh dijelaskan sedikit nih, Prof. Bambang, bocorannya nih ya.
Ya, Profesor Yann LeCun akan membahas tentang self-supervised learning, salah satu metode pembelajaran mesin dan AI yang terkini, gitu, yang merupakan salah satu metode yang dipergunakan untuk menangani persoalan data yang tidak menggunakan label atau tidak memerlukan anotasi yang dilakukan oleh manusia. Jadi kita akan belajar banyak dari beliau, dan teknik self-supervised learning ini dikembangkan begitu karena tersedia berlimpah data di internet, di organisasi dan sebagainya yang merupakan data-data yang tidak berlabel. Perkembangan deep learning sejauh ini itu dikombinasikan dengan supervised learning untuk mengembangkan model AI yang cukup baik begitu dan memiliki kinerja yang cukup bagus, tetapi memiliki kelemahan yaitu anotasinya atau labelingnya itu dilakukan oleh manusia. Jadi kalau kita ingin mengatasi masalah itu, maka diperlukan metode baru, dan self-supervised learning itu merupakan salah satu jawaban untuk persoalan ini.
Oke, baik. Ini mengenai the future of machine and deep learning. Mungkin the future of machine ini, how is it, Prof. Bambang? Seperti apa ini untuk orang awam begitu ya, seperti saya? Mungkin bisa diberikan gambaran?
Ya, jadi mungkin kita mulai dari pengembangan model AI, misalkan untuk mengenali wajah manusia atau mengenali objek di dalam foto, misalkan begitu. Jadi untuk membangun kemampuan mesin yang secara otomatis dengan kameranya untuk dapat mengenali misalkan wajah manusia atau satu objek tertentu di dalam foto, apakah itu
jadi,
misalkan
saya ada dua data, satu rata
atau maka diperlukan sedemikian banyak data training untuk membangun model AI itu, dan data training ini memerlukan semacam anotasi atau label. Jadi kita memberikan semacam supervisi bahwa foto yang bersangkutan adalah wajah si A misalkan, dan foto yang lain adalah wajah si B. Dan itu kemudian kita ajarkan kepada model AI kita supaya model AI kita itu pintar di dalam mempersepsi atau di dalam memahami foto wajah seseorang gitu. Nah, pekerjaan untuk menganotasi foto-foto tadi sebagai wajah si A, si B dan seterusnya itu secara tradisional itu dilakukan oleh manusia, dan itu memerlukan waktu serta biaya yang cukup mahal gitu. Dan oleh karena itu kemudian diusulkan satu metode yang dikembangkan dalam beberapa tahun terakhir ini, bagaimana kalau kita tidak perlu atau tidak usah menggunakan metode labeling yang dilakukan oleh human tadi, dan meminta komputer untuk mengenerate, untuk membangkitkan secara otomatis anotasi dari foto atau data yang diajarkan. Jadi gagasannya secara sederhana seperti itu.
Baik, Prof. I think Prof. Yann LeCun is joining. Betul ya?
Yes, good morning. Yes.
Hi.
Oh, good morning,
Hi,
Professor
Prof.
Yann LeCun.
How are you?
Okay.
Hello, how are you, Prof?
Hi.
What time is it now there?
It's 10 p.m. and there was some confusion because I was told it was at 11 p.m. So I didn't realize, I thought it was an hour from now.
Oh, oke. Kita bisa memulai sekarang, Prof. Bambang. Baik, saya serahkan langsung kepada Prof. Bambang untuk Keynote session yang ketiga. Silakan.
So, good afternoon, Professor Yann LeCun. I will be serving as a moderator of your session, and I already read your CV. So, without further ado, let me start the session. So you will have 60 minutes in total, consisting of 40 minutes for presentation and followed by 20 minutes of a Q&A session. So the floor is yours. Thank you.
Thank you very much. Good morning. For me, it's late evening. I guess I should say selamat pagi. It's really a pleasure to be here. I wish I could visit Indonesia. I've never been there, and I'm told it's absolutely beautiful. I hope in the near future I'll be able to visit. So I'm really excited to see that the digital economy is taking off in Indonesia, and it's really a pleasure to to talk to the community here in Indonesia, which I understand. I looked at some of the posters in the virtual room, what people are trying to do with machine learning and AI, and it's fascinating. As you know, Facebook has a big presence, of course, in Indonesia, but also is investing in companies in Indonesia like Gojek. In fact, a company I co-founded called Element is very present in Indonesia, has partnered with Bank BRI and Bank BCA and Telekom Indonesia and GDP Venture. And it's been a real pleasure to collaborate with everyone in Indonesia. Okay, so let me share my screen so I can, let's see. All right, I hope you're seeing this.
Yes.
Wonderful. Okay, so I'm going to talk about self-supervised learning mostly, and which is kind of the new hot topic in AI and machine learning. And a little bit about the present, the state of the art, and the future of machine learning. What are the challenges ahead? Okay, so a lot of the success of machine learning so far have been due to supervised learning, right? So supervised learning is the paradigm by which let's say you want to train a machine to recognize images, classify images of cars from images of airplanes. You show an image of a car. If the machine says car, you do nothing. If it doesn't say car, then you change the internal parameters of the machine so that next time around that you show the same image, the output is closer to the one you want. Okay, so you tell the machine what the correct answer is. And if you have enough data, and if the neural nets or the learning machines you're training are sufficiently powerful, this works really well. So you can do speech recognition, image recognition, face recognition. You can generate captions for images. You can classify the topic of a text. You can even translate text. This works really well. And it's based on, of course, an old idea of machine learning, which goes back to the 1950s. And traditionally in machine learning, you would take an image and you would feed it to a so-called feature extractor that would be sort of engineered by hand. And then this would be fed to a classifier that would be trained. What deep learning changed is the ability to train the system completely end-to-end. So a deep learning system is called deep simply because it has multiple layers. And every single layer in the system is trainable. And so the system learns the task of recognizing an image, for example, from the raw pixels all the way to the categories at the end. And that's really the innovation in deep learning. The idea goes back to the 1980s. But the sort of the practical applications have really blossomed in the last 10 years or so. So the reason why you want multiple layers is because the perceptual world is compositional. And so there is an advantage to representing images or text or speech or any kind of signal, natural signal, in a hierarchical manner where motifs at a low level are detected and then combined to form higher level, more complex motifs. And then as you go up in the layers, you get representations that are more and more abstract. So that's really sort of the basic principle of deep learning. Now, in traditional deep learning systems, the functions that are implemented inside of the neural net, as many of you know, I'm sure, are basically as very simple. The first set of functions are basically weighted sums, and the second set of functions are pointwise nonlinearity. So you can think of every unit in a deep learning system as being a unit that computes a weighted sum of its inputs, which are the state of the unit at the previous layer, and where the weights can be seen as coefficients in a weight matrix, essentially. So the state of the system of one particular layer is a vector. You multiply this vector by a matrix, you get a new vector. That's a linear operation. And the weights of this matrix is what is going to be subject to learning. And then you pass the results, the components of the resulting vector through nonlinearities, similar to the one that is shown here on the top right, which is a half-wave rectification, which in neural net lingo is called a ReLU. So you stack multiple alternate layers of matrix multiplication, linear operations, and pointwise nonlinearities like this ReLU. And as you stack more and more layers, the system is able to represent more and more complex functions. So you train the system end-to-end to adjust all the parameters in all the weights in all the matrices so that the input-output function does what you want. So that's a very simple concept. And it's using the idea that you can compute the gradient of a loss function that measures the discrepancy between the output you want and the output you get, using a method called backpropagation, which is nothing more than a practical application of chain rule. I'm not going to go through the formulas. They are actually just expressions of chain rule, which is a very simple mathematical concept that a lot of us learn in college or sometimes even in high school. And And based on this principle, you can, these very simple equations, you can backpropagate signals through the network by basically going backwards from the signal that is used to compute the output and compute the gradient, which are derivatives, essentially, of the loss function with respect to all the parameters in the system. So it tells you by how much and in which direction to modify each of the coefficients inside of this neural net so as to make the objective function, the loss function, smaller. Okay, so that's the idea of gradient-based learning, and of course, you know, as I said, it goes back to the 50s. The idea of stacking multiple layers goes back to the 1980s. Now, in recent years, or you know, in the last 10 years or so, there's been sort of a generalization of this to sort of complex networks of functional modules. So what deep learning has become nowadays is perhaps should be called differentiable programming. So you essentially write a program in Python or some other language that defines a graph of functions but those functions are not entirely determined. Their precise function depends on a bunch of free parameters that can be learned through gradient descent, essentially, through gradient-based learning. So you assemble, so the engineer in deep learning or machine learning designs this architecture by assembling modules. And in systems like PyTorch, for example, or TensorFlow, the gradients are computed automatically. So you don't have to worry about how you compute the gradient. You just write the program that essentially computes the output of your network, and automatically the system will produce a function that computes the gradient of whatever loss function you want with respect to the parameters in your system. So that makes it very, very convenient to engineer a machine learning system by just assembling functional blocks. And a lot of the innovation in deep learning actually consists in kind of devising new architectures of this type. So because the architecture is basically determined by a program, and the program could determine the architecture in a data-dependent way, the architecture of the network is not necessarily fixed. And so people have kind of called this differentiable programming, the idea that you write a program whose function calls are not entirely determined, but whose function is finalized by learning. Okay, so let me talk about three main challenges that AI is facing today. And after a brief review of current state of the art, I'll talk about how to address the first two. The third one, I have no idea how to address. So the first challenge really is being able to learn tasks with few label samples. Okay, currently to train a computer vision system, you need millions of examples. Or to train a translation system, you need, you know, hundreds of thousands, if not millions, of sentences that have been translated from one language to another. And that makes it difficult to apply deep learning to a lot of different situations for which you don't necessarily have the possibility of collecting all the data. So for this, I'll be proposing self-supervised learning. The second problem is learning to reason. So deep learning systems at the moment are very sort of reactive. They compute their output with a fixed number of steps, which is the number of layers. But you'd like to be able to build machines that can reason, that can sort of think about how to produce an answer before producing it. And in humans, we observe this too. There are certain tasks that we can do very fast, and then certain tasks that we have to kind of think about before we can solve them. But before I talk about this, let me talk a little bit of history and a little bit about the state of the art. So convolutional nets, which I'm sure many of you have played with, is a particular way of connecting the units in a neural net. So a particular way of restricting the linear functions, the matrices, to make them sparse in such a way that the system is particularly well suited to processing images or speech or audio or natural signals or video or things like that. So in a convolutional net, units are connected only to sort of a local neighborhood on the previous layer, and then you stack multiple layers, and as you go up the layers, the resolution goes down, and the number of feature maps, the number of different features that are extracted by the system sort of goes up. And this is very much inspired by the architecture of the visual cortex. So back in the 1990s, when I was working at Bell Labs, we were able to build systems of this type that could recognize handwriting. So this is an example of one of those, where it is shown a handwritten character here on the left, and then each column from left to right is a different layer in this neural net. And by the time you get to the top layers, the representation of the input image is very kind of abstract, and the system is able to kind of recognize simple characters. This is me when I was young, about half the age that I am now, and this is actually my phone number when I was at Bell Labs in New Jersey. So I hit a key and the camera grabs an image, and then the neural net running on a computer kind of recognizes those characters. So this was working really well. Very quickly we realized that we could use this to also recognize multiple objects, and that turned out to be really useful afterwards. Okay, so then many years passed. There was some progress, but mostly neural nets didn't interest many people between the mid-90s and the mid-2000s. And then, but we were able to do things like, recognize checks and things like that. But what happened around 2010 or so is what could be called the deep learning revolution. So people started paying attention to neural nets and deep learning, particularly convolutional nets, because the computers were becoming faster, the data sets were becoming bigger, and there were new ideas that we'd come up with in the meantime that made those systems work for relatively deep systems. And so that created a revolution. So this is an example of a convolutional net. Not all of it is represented because it's too big, but which basically is trained to recognize natural images, objects in natural images. Typically nowadays, those neural nets have between 1 and 100 billion connections. Fewer parameters than that because some of the weights are shared. And they can, they recognize images very well, as many of you know, and they're used very, very widely by companies like Facebook and Google and Amazon and IBM, Intel, and just about everybody else, Microsoft. So the applications of this are very wide. Of course, in driving assistance, not yet completely autonomous driving, but certainly driving assistance, in medical image analysis for detecting tumors and things like that, and a lot of other applications that are being deployed. So computer vision has progressed a huge amount. Modern computer vision systems based on convolutional nets are able to do things like segment every pixel, basically label every pixel of an image with the category of the object it belongs to. So this is called panoptic segmentation. And this works really well. There's a lot of open source code to do this from Facebook and various other sources. This picture is from a system from Facebook called Detectron 2, which can be just downloaded. It's open source. A lot of applications in medicine and content filtering. So companies like Google and Facebook are built around deep learning nowadays. You take deep learning out of Google and Facebook, and the two companies crumble because all of the sort of content ranking and filtering is essentially built around deep learning. This little work that I'm showing here on breast tumor detection, breast cancer detection, is by some of my colleagues at NYU. Very interesting work. It's also open source. This is another piece of work for medical imaging, which is actually a collaboration between Facebook and NYU on accelerating the process of taking images for MRI exams. So let's say you need an MRI, you have to sit still in an MRI machine, which is very noisy and uncomfortable for perhaps up to an hour. And this system allows to reduce the time it takes to collect the data by a factor of 4 without degradation in the quality of the image. So now an exam that used to take an hour can take 15 minutes, which means it's cheaper, more people can have it, and the quality is the same. And it's using convolutional nets of a particular type called UNet, and sort of various other tricks. So this may revolutionize medical imaging over the next few years. Those are still experimental systems, but they're sort of being tested. There's a lot of applications of deep learning in science, and this is a slide of a piece of work from Eichenberg et al. A few years ago on basically trying to understand what the visual cortex is doing by having a model of the visual cortex, which itself is a convolutional net, and then trying to explain what we observe in the activity of the brain in the visual cortex with what we observe in convolutional nets. And the convolutional nets basically are the best models we have to explain how vision takes place in the brain. Other applications of deep learning for science include things like physics, cosmology in particular. You can train a neural net, a convolutional net in this particular case, to approximately solve a partial differential equation, which would otherwise take too long. And so it sort of accelerates the process of simulating the early instance of the universe, for example. People are using this also for designing new materials and figuring out the structure of proteins, analyzing high energy physics experiments, etc. Okay, so deep learning is used everywhere, as you know, and the deployment has been very, very fast. It is now the case that when a new innovation pops up in a paper, a preprint on archive, very often, if that technique is good, it's going to be picked up by all the major companies, and it's going to be deployed in their services within 6 months. The path of technological deployment is extremely fast. What's going to happen, though, over the next few years is that there's going to be an increasingly large use of deep learning at the edge, which means deep learning systems are going to be run on smartphones, on wearable devices, on augmented reality glasses, on virtual reality goggles. So there's going to be a lot of embedded deep learning just about everywhere. Okay, so let's go back to the 3 challenges now. Now we've talked about the state of the art. What are the challenges for the future? I'm first going to talk about the problem of learning to reason. So really, this is sort of within the broader context of new deep learning architectures. One type of architecture that has really had a huge impact over the last few years is the idea of building a neural net not just as a sequence of matrix multiplication and nonlinear operations, but have modules inside of the neural net that basically behave like associative memories. So the way those modules work is that there is a vector that comes in that we call an address, X. You compare this address with a bunch of key vectors by just computing the dot product between the address and the vectors. So they give you a bunch of scores, and then you pass those scores through what's called a softmax function, which take the exponentials of each of the scores and then normalizes them by the sum. So what you get is a bunch of coefficients between 0 and 1 that sum to 1. And you use those coefficients to compute a weighted sum of value vectors, right? So the output is really is a weighted sum of the values, where the weights are the coefficients coming out of the softmax. And this is really essentially kind of a soft associative memory. The idea for this module goes back to a paper by some of my colleagues at Facebook, Jason Weston and his colleagues, 6 years ago, called Memory Network. And there were kind of various other examples of this afterwards. And this type of module has been kind of used very widely in an architecture called transformer. So a transformer is a type of neural net architecture where basically each group of units, each group of neurons, if you want, in a layer is one of those kind of associative memory. But it's designed in such a way that the output is equivalent to a permutation of the input. So if you have a transformer, you can do a permutation of the inputs, and the output will be permuted the same way, but otherwise unchanged. This is called equivariance. And the advantage of this is now what you have is a neural net that basically works on sets instead of working on sequences or images, or kind of taking advantage of the topology or the geometry of the input. It ignores it, and that's advantageous for a lot of things. I'll come back to this in a second. So this is an example of a recent computer vision system that from Nicolas Carillon et al. So this is a group from Facebook AI Research in Paris. It's a system called DITER, and it's available in open source. And it's very interesting. It has a front end which consists in a convolutional net looking at an image, and then it's followed by 2 of those transformer type networks. And what the transformers are doing is basically doing sort of object-based reasoning, if you want. They can reason about where the object is, what are the relevant parts of the object that the system should pay attention to. And so you can see the result here where it identifies 2 elephants. The baby elephant is in front of the mother elephant, and but the system is able to tell that there is two elephants, one of which is in front of the other. So I don't have time to explain here exactly how this works, but I really encourage you to kind of look at this URL and either or the paper. And this is, in my opinion, the future of computer vision is going to be systems like this that are trained end to end to do object detection, localization, and things like semantic segmentation. So this is examples of outputs of the DTER system. When they're applied to images, they can label every pixel in the image with the category that of the object that this pixel belongs to, and produce masks for every object. This is really amazing results, which I think people would not have expected just 5 years ago. Let me skip ahead a little bit. Okay, now here's the big challenge. Humans and animals learn incredibly efficiently, and we're not able to reproduce the type of learning that we observe in humans and animals in machines currently. And so what it is that allows humans to learn so efficiently. So if you look at what age babies learn basic concepts, babies learn an enormous amount of background knowledge about the world in the early weeks and months of life. So in about 3 months, babies learn about the difference between animate and inanimate objects. In about 6 months, they learn about like basic intuitive physics properties like stability of an object. They know if an object is going to fall, for example, when you put it on the ground. But it takes about 9 months for babies to learn about things like gravity and inertia. So the fact that an object that is not supported falls, babies that are 10 months old know about this. If they see an object that floats in the air, they would be very surprised. Younger babies, younger than 7 or 8 months, have not yet understood the fact that objects are supposed to fall. So they're not surprised when they see an object apparently floating in the air. So what type of learning do babies and baby animals also use when they learn everything about the world? And perhaps the accumulation of this background knowledge that babies and young animals learn by observation constitutes the basis of common sense. Common sense is something we'd like our machines to have, but currently they don't. The most intelligent of our machines don't have as much common sense as a cat. Okay, so what I'm proposing as an approach to this, and this is very much kind of aspirational, is the idea of self-supervised learning. So what is self-supervised learning? It's the idea that you show the machine during training, you show it a piece of data, and the machine pretends that there's a piece of that data that it knows and another piece that it doesn't know. So let's say, for the sake of example, that we're going to train the machine to predict what's going to happen in a video. So you show a few frames of a video, for example, this little girl here with a birthday cake, and you ask the machine, predict what's going to happen next. You don't show the machine what happens next yet. You just ask it to predict. And then after the machine has predicted, you show it what actually occurs, and the machine kind of corrects itself to make do a better job at prediction. So stated like this, it looks just like supervised learning. And in fact, it's very much like supervised learning, which is why I call it self-supervised. The difference with supervised learning is that you don't have any external signal to train the system that has to be produced by human labelers. Here, the supervisory signal is the input itself. Okay, so hence the name self-supervised. Now, the example I gave was for predicting future frames in a video, but you could imagine using this for predicting missing frames in a video or missing pieces of audio, missing words in the text. And basically what self-supervised learning consists in is filling in the blanks, okay? You show the system a partial input and you ask it to predict the missing part of this input. In some cases, you know in advance which parts are visible and which parts need to be predicted. In some cases, you don't know. You won't know until you're shown the example which part of the input will be visible and which one will not. And that's the difference with supervised learning. So you can use self-supervised learning for two different things. Either to learn features, so basically you use a self-supervised task to train a machine to just represent the world, and then you use the representation learned by the system as input to a subsequent supervised system. This is learning representations, where self-supervised learning is used as pre-training to precede supervised or reinforcement learning. And then the second use is to learn predictive forward models of the world. So if you have a robot or a system that is supposed to kind of produce some control, if the system is to be able to do a good job at producing a sequence of action that arrives at a particular goal, it needs to be able to predict the consequences of its actions. And for that, it needs a model of the world that allows it to predict what's going to happen as a consequence of its actions. The main question in all of this, in self-supervised learning, is how to represent uncertainty and multimodality in the prediction. And for this, I'm proposing the idea of energy-based models. So this is very much like probabilistic modeling, except it's a little weaker, and it allows us to, it gives us more flexibility, if you want. So what is the idea of energy-based models? So the idea is that, let's say you have two variables, x, that you observe, and y, which is a variable you want to predict. Your learning machine will compute a scalar value, which is going to be f of xy, and f of xy is going to take low value if y is compatible with x, and a larger value if y is not compatible with x. So if x is a piece of a video, and if y is a good continuation of that video, then f of xy takes a low value. If y is not a good continuation of the initial segment x, then f of xy will take a large value, okay? And f of xy is going to be computed by a neural net, which we're going to have to train. So here's an example here at the bottom. Here are two energy functions. Here, x is a scalar value and y is a scalar value. And the little blue dots represent training samples. So you want low energy for the training samples, and you want higher energies for everything which is not a training sample outside the manifold of training data. And the two energy surfaces that are represented here are two equally good energy surfaces. So we have x and y's. We have an energy function that sort of captures the dependency between x and y. And the way we do inference is that if I give you a y, you give me a set of, if I give you a value for x, then you give me the corresponding value of y that minimizes the energy for this particular value of x. That's inference, okay? We haven't talked about learning yet. So now let's talk about learning. How do you train an energy-based model? To train an energy-based model, you have to make sure that the energy of the training samples is low. So the energy that your model gives to a training sample is low. And then the energy that your model gives to everything else is higher, okay? There are two types of methods. The first type of method is contrastive methods. They're intuitively the easier to understand. You basically take a point, a data sample, you change the parameters of the energy function so that its energy goes down as much as possible. Then you take another point, random or not random, somehow picked outside the manifold of data, and then you push its energy up, okay? And you do this using various loss functions that measure, the difference between the energies or something like that. So that's the first type, contrastive methods. There's another type called regularized architectural methods. I'm not going to explain now how they work. I'll do this in a minute. So this is a bit of an eye chart, and I don't expect you to read all of it, and I'm not going to go through all of it. But basically, I've listed a whole bunch of traditional learning methods and classify them as to whether they are contrastive or regularized or architectural. So things like maximum likelihood, contrastive divergence, metric learning, Siamese networks, generative adversarial networks, etc. Those are all contrastive methods. Also, masked autoencoders that are used in the BERT system, which I'll talk about in a minute, are also contrastive. And then there are other methods here in the regularized things that I'm not going to go through, except two sparse autoencoders and variational autoencoders, which are two popular methods that I'll go to in a minute. So let me start with something called denoising autoencoder, which is a contrastive method, and it's extremely successful, very powerful, and used very widely to train natural language processing systems. So you take a training sample Y, let's say a piece of text, and you corrupt it. And the way you corrupt it is a piece of text is that you remove some of the words in that text. Typically, let's say 10 to 20% of the words. By removing, I mean you substitute the words by a marker that indicates sort of a blank marker. So now you have the sentence X with holes in it. You run it through a neural net, and you train this neural net to recover the missing words. Okay. And this can actually be formulated as some sort of contrastive learning process which I'm not going to go exactly into. But by training a system of this type, particularly if you use the transformer architecture inside of the network, by training a system to predict the words that are missing in millions of text, typically a few hundred words long, the system basically has to learn good representations of word that allows it to make that prediction. So if I say a sentence, the blank chases the blank in the kitchen, you can probably infer that it's probably a cat and a mouse. If I say the blank chases the cat in the mouse in the kitchen, you know the blank is cat, okay? Because you know by the context, right? So those systems are able to do this as well. They kind of learn how to fill up the missing words, and in the process of doing so, they learn good representations of text, to the extent that now those systems basically beat everything else that we have. So this approach of denoising autoencoder approach to pre-train a text understanding system are basically beating all the records in natural language processing, and have revolutionized natural language understanding over the last 2 years. So this was some work by at Google, Wadzwani, who et al., who proposed the transformer architecture, and then the BERT model, which was this idea of using self-supervised training, was proposed by Devlin about 2 years ago. Now, those systems, this kind of system have been used for all kinds of stuff, particularly translation. So the best translation systems at the moment are giant transformers that have multiple encoders for multiple languages and multiple decoders for multiple languages. And they can, the latest system from Facebook, for example, can translate 100 languages into 100 other languages, or I mean the same 100 languages very well. And it's superhuman in the sense that no human that I know of is capable of translating 100 languages into 100 languages. So those things work really well. A similar system, this is work by Guillaume Lample and François Charton at Facebook AI Research in Paris. They've been able to train one of those transformers to solve differential equations, to compute integrals symbolically. And those systems actually work somewhat better than sort of handcrafted algorithms that you can find in Mathematica, MATLAB, or Maple. This is really impressive and completely unexpected. So a lot of really impressive stuff. Here is a dialogue. This is a system built at Facebook in New York, and this is a system that can look at an image, and then you can hold a dialogue with that system about the image. So on the left here, they talk about this teddy bear in a trash can, and the dialogue here takes place on the left below. And I challenge you to tell which of those two is the machine and which of those two is the human. The human is actually in blue and the machine in gray, but it's very hard to tell. So now a progress that's happened over the last year or so, or 2 years maybe, is using self-supervised learning for learning features for images. And for images, it's more difficult to do because the same procedure that is used for text doesn't work very well, because there is a lot of uncertainty in sort of reconstructing patches from an image, which basically make it very difficult to train those systems to fill in the blanks. So what has worked for learning features for images is what's called contrastive embedding. Essentially, what you have is a pair of two identical neural nets, and you show those two neural nets two images that are essentially distortions of each other. And you train the two neural nets to produce two vectors that are very, very close. Okay, so there's a cost function that says, here are two images, produce two outputs that are very close to each other. Then you show a pair of images that are different, and then you have another loss, a term in the loss function that pushes those two vectors away from each other. This works really well for things like face recognition, and there's a number of work, Pearl, Moko, that came from Facebook, and SimClear that came from Google to make this work very well. But it's very expensive. It works really well for speech recognition as well, but it's very expensive computationally. It takes, it would take millions of dollars to kind of pay for a cloud service to train one of those neural nets to do a good job. So what's happened in recent months, really this year, is two different ideas, one from Facebook called Deep Cluster, another one from DeepMind, actually called BYOL, Bootstrap Your Own Latent. And I'm not going to explain exactly how those work, but they're based on this, contrastive, on this sort of Siamese net, parallel neural net, if you want, that share the same weights. But you don't need this contrastive phase where you have different samples that need to be pushed away. And the reason why this works is not actually entirely clear, at least for the case of BYOL. It's much clearer for the case of Deep Cluster. But those systems basically have the record at the moment. So if you train those systems completely unsupervised to represent images with this sort of idea of, distort an image, produce representations that are similar or identical for distorted images, and then you use the representation as input to a linear classifier to recognize ImageNet, for example, objects from ImageNet. You get performance that approaches the performance of systems that are trained entirely supervised on ImageNet from scratch. So that's really impressive because that means we're going to be able to use self-supervised pre-training to train image recognition systems. And people are trying to apply this to video and all kinds of different things. Let me skip ahead a little bit. Okay, so an interesting set of architectures is what's called latent variable energy-based models. And this is the type of architecture I'm mostly interested in at the moment. So you have an observation X, it goes through a neural net that I call a predictor that predicts that produces a representation. And then this goes into a decoder. And the decoder combines that representation H with what's called a latent variable Z, so as to make a prediction. The problem with predicting future frames in a video, for example, is that there are many, many different ways the video could go, right? There's many plausible futures to a particular segment of video. And you'd like the machine to be able to predict all of those possible futures or represent the set of all possible futures. So the way you represent a set is that you allow the latent variable to vary over a set that is predetermined. And then you train the machine to make the overall prediction vary over the desired set of plausible prediction as the latent variable varies over the predetermined set. If this set has a particular distribution, you will also get a distribution on the output. So this is the idea of latent variable models. And it's an idea that's used in GANs and other type of models. But one idea here is to use what's called regularized latent variable models. And I don't have time to go into the details of this, but it basically consists in training the system consists in showing an X and a Y, a pair of X and Y, then finding the value of Z that makes the best possible prediction. Okay, you can do this by gradient descent, for example. If you do this, unfortunately, the system can predict lots and lots of different things that may be completely nonsensical. So you need to regularize the latent variable in such a way that it has a limited information capacity so that it can only predict a limited amount of different things, and it will train itself to just predict the things that it is being trained on. So this is still work in progress. There are several ways to do this capacity limitation. And one particular example of this is variational autoencoders, which I'm not going to explain, other than to say that you can use them for video prediction. So let's say you have a short segment of video go through a predictor, and then the rest of the video goes through an encoder, which produces a prediction for the latent variable, which is used to then reconstruct the prediction. And if you limit the information content in the latent variable, the system will be able to do a good job afterwards. So this is called a conditional variational autoencoder if you do it in a particular way. That's an example of so this is an example of variational autoencoder that is trained to predict what cars are going to do on a highway. All right, so there's a camera looking at a highway, it's looking down, and what the camera has recorded is on the left column. And what you see, the four columns on the right represent different predictions that are performed. Let me play this again. Different predictions that are performed by the system by choosing the latent variables in different ways. So depending on the latent variable, you will get different predictions for that video. And if you don't allow the system to use a latent variable, what you get is the second column from the left, which is very blurry. The system cannot actually make multiple predictions, so it has to make one prediction, which is the average of all the plausible scenarios. And that turns out to be a blurry prediction, which is not good. You can use this system to train a car to drive itself, actually. Okay, so this is an example of such a system. So using this prediction of what cars around you can do, you can train a system to kind of drive safely or to plan how to drive safely. So it's basically imagining in its head what the cars around it can do, and then it trains itself to kind of produce an action that will minimize the number of collisions, essentially. So what you see here is the car that our system is driving is the blue car, and the little white dot indicates whether this car is accelerating, braking, or turning. And the green car around it are recorded cars from a highway. And the bad news here is that the blue car is invisible to the green cars because the green cars are recorded. But the blue car, manages to kind of escape. Okay, so let me conclude so we can have some time for questions.
Yeah.
So self-supervised learning is the future. There's no question about this in my mind. One thing I should mention at the bottom here is that we hear a lot about artificial general intelligence. In my opinion, there is no such thing as artificial general intelligence. Intelligence is always specialized. Even human intelligence is very specialized. So we should talk about human-level intelligence or maybe cat-level intelligence rather than artificial general intelligence, which is a concept that does not exist. Thank you very much for your attention, and I'm looking forward to your questions.
Thank you, Professor Yann LeCun, for your inspiring talk. Now we proceed to Q&A session. And I have already a few questions. The first questions comes from a professor from a university in Indonesia. So the question is, self-supervised learning seems to have a similar goal with less than one-shot learning, which is trying to tackle the data-hungry phenomenon of deep learning paradigm, as well as trying to fill in the blank data. Are you considering your self-supervised learning approach better than that other approach in such context? In which aspects?
Yeah, I mean, self-supervised learning really should be seen as sort of a paradigm rather than a particular approach. So you can formulate a lot of what people are doing already as a form of self-supervised learning, and I think it's a particularly good approach to things like not zero-shot learning, but few-shot learning, let's say, and that's typically the scenario where those things are used, where you pre-train the system in a self-supervised manner to basically fill in the blanks, or you use a pretext task of some kind, and then you use the internal representation learned by the system as input to a subsequent supervised learning system. It's always a few-shot, right? It's not completely zero-shot in the case.
Okay, thank you. And the second questions, are supervised learning, unsupervised learning, and semi-supervised learning, as well as reinforcement learning, different facets of one complex process, or they are fundamentally different? If they are parts of the same process, is there any attempt for building universal learning theorems? And if they are not part of the same process, how can organism cope with such complexities?
Right. Okay, so I mean, there are certain, I don't think there is a general theory, right? I mean, there is a general theory of supervised learning. There is not much theory of self-supervised or unsupervised learning, although to some extent, self-supervised learning is just a form of supervised learning. So, so perhaps the theory could apply there. So basic theory, like the Vetnik-Chervonenkis statistical learning theory, applies to basically all scenarios. Now, what is different about reinforcement learning? So reinforcement learning is very inefficient in the sense that the signal that is given to a reinforcement learning machine is not the output you want, but is an indication of whether the output produced by the system was good or bad, right? That's the reward, if you want. Okay. And the function that computes this reward is not known, it's not differentiable, which means the system cannot estimate the gradient of in which direction it should change its parameters to kind of make the output better. It has to try something, to get the reward back. A lot of interesting approaches to reinforcement learning actually consist in training a differentiable neural net to predict what the value function is, so that you can actually back propagate gradient through it. That's called the actor-critic approaches. So in some sense, you could view a lot of those things as energy-based learning, and a lot of them are actually can be viewed as contrastive learning, including in the context of reinforcement learning. Another characteristic of reinforcement learning is that, contrary to the hypothesis you make in supervised learning, the examples you see are not independent. The example you're going to see at time t+1 depends on the action you took at time t. And so that means the examples are correlated. And that makes the problem more difficult to solve, essentially.
Okay. Next question is in regard to your energy-based approach that you presented in your talk. How you compare your approach with other contrastive representation learning, such as SIN, CLR, MoCo, and with those based on generative models such as BERT, GPT, in terms of its capability to handle a large amount of unlabeled data. But I noticed that you already mentioned in your presentation that contrastive model is just a special case of your more general energy-based approach. Can you
that's right.
make some comments on that?
So that's right. I mean, energy-based model is really kind of a way of sort of describing all of those methods in sort of a unified conceptual framework, if you want, right? So contrastive learning is a particular way of shaping the energy function, and then there are non-contrastive approaches. And, Pearl, MoCo, Seem Clear, etc., are sort of different ways of doing all of this.
Okay. And because we have a limited time, it is the last question. You once said that the self-supervised learning will only reach its potential once it can reason like a human. To your opinion, how long it takes for self-supervised learning to reach human level intelligence? Maybe
I wish I knew. I wish I knew. I don't. Okay, yeah. I mean, there's the two problems I mentioned are really the two problems we need to solve, right? So the first problem is finding good ways to do self-supervised learning. I proposed, there's a few that I listed here, most of which don't come from me, right? They are techniques that other people invented, or maybe techniques that were inspired by some of my work, from many years ago. Things like Siamese networks and this kind of contrastive embedding, for example. But so the main issue there in self-supervised learning is how to handle uncertainty in the prediction, right? So self-supervised learning is filling in the blanks. When the blanks, where there's lots of plausible blanks, lots of different ways you could fill in the blanks, then you need a way for the machine to represent all those options. And there's only two ways I know. One way is using this kind of joint embedding. The other way is using those latent variable models. Okay. And we haven't really figured out a good recipe for doing this, actually. I'm not satisfied with any of the things that I told you about. I think we need to find a better way of doing all of this. Right? So that's the first question. And then the second question is, we also need machines to be able to reason. And once we've figured those two things out, then we're going to be able to train machines to by just watching video, and maybe they will acquire common sense because they will be able to learn everything there is to learn about the world, like babies.
Okay.
This may take 2 years, 5 years, 10 years, 20 years. I have no idea.
Okay.
Maybe it'll come from some of the people watching this in Indonesia.
Yes. Okay. Thank you, Professor Yann LeCun. So, ladies and gentlemen, now we come to an end of this session. On behalf of the organizing committee, I would like to express my highest appreciation to Professor Yann LeCun for his insightful and excellent talk. Thank you for participating in today's webinar. We hope to see you again next time.
Thank you very much. It was a real pleasure.
Professor Yann LeCun. Let's
Thank you, Professor Yann LeCun.
Professor Yann LeCun.
Thank you so much.
Thank you so much.
On behalf of BPPT, I would like to appreciate your time and your sharing with us all in the AI Summit 2020. It was really a pleasure for us. Thank you so much. Hope to see you here in Indonesia very soon. Next time, next year probably.
I hope to come in person at some point. Yes.
Yes.
Thank you, Professor Yann LeCun.
Thank you.
Ya, terima kasih untuk Prof. Bambang Riyanto Trilaksono yang sudah memandu ya keynote session yang ketiga tadi bersama Prof. Yann LeCun. Also thank you for staying up late ya for us di Inovasi Indonesia Artificial Intelligence Summit 2020. Dan untuk selanjutnya ya, untuk keynote session yang selanjutnya kita akan membahas mengenai AI Computing Platform. Dan nanti akan disampaikan oleh Kit Schreier yang merupakan VP Worldwide AI Initiative NVIDIA Corporation. Dan moderator kita pada keynote session yang berikutnya adalah Dr. Eng Ayu Purwarianti SDMT. Selamat pagi menjelang siang ini ya untuk Ibu Ayu.
Selamat siang Mbak Nara.
Selamat siang, lebih enak ya, sudah jam 11, enaknya siang ya Bu Ayu. Sehat Bu?
Ya. Insya Allah.
Baik, saya akan membacakan terlebih dahulu Ibu Ayu untuk CV Ibu Ayu ya. Ibu Ayu Purwarianti ini menyelesaikan S3 di bidang Natural Language Processing sebagai bagian dari Artificial Intelligence di Toyohashi University of Technology. Kemudian S1 dan S2-nya di ITB. Dan saat ini Ibu Ayu mengemban amanah sebagai Ketua Pusat Artificial Intelligence ITB dan Ketua Program Studi S3 Teknik Elektro dan Informatika ITB. Sebelumnya, Ibu Ayu ini pernah memegang sebagai Ketua Program Studi S1 Informatika ITB dan mendapatkan penghargaan sebagai Ketua Program Studi Nasional kedua. Selain di ITB, Ibu Ayu juga berperan sebagai co-founder Prosa.ai dan aktif di INACL Indonesia Association for Computational Linguistics ya. Kemudian juga IAIS Indonesian AI Society, kemudian juga Indonesia Accreditation Board for Engineering Education, terutama di Computing Committee. Baik, Bu Ayu sudah siap untuk membawakan keynote session kita AI Computing Platform? Baik, kalau begitu silahkan saya serahkan langsung ke Ibu Ayu.
Ya, terima kasih Mbak Rara. Thank you Mbak Rara. Okay, good afternoon all. Selamat siang. Assalamualaikum warahmatullahi wabarakatuh. Hi Kate.
Hi, how are you?
Hi, I'm fine. It's a great honor for me to share this keynote session of your from NVIDIA with title of AI Computing Platform, right? So before we start the session, I would like to read your CV as follows. Okay, wait a minute. Okay, Kit Schreier is Vice President Worldwide AI Initiatives at NVIDIA with a primary focus on helping governments advance their national AI programs by harnessing the power of accelerated computing, artificial intelligence, and autonomous machines. Kate leads NVIDIA's global public sector portfolio and AI Nations Initiative, advising government leaders on the domestic AI infrastructure needed to achieve national AI objectives. So it's very needed for Indonesia. Before joining NVIDIA, Kate was senior partner at EY Consulting and served as the founding global AI practice leader. And also prior to EY, Kate was a senior partner at Deloitte Consulting and served as the first global chief digital officer driving the vision and implementation of a digital workplace for 250,000 employees. Oh, that's a lot. Kate has been a guest speaker at universities and industry conferences from Shanghai to Tallinn to Riyadh and also to Indonesia now, right? And has also served as a guest facilitator for Harvard Medical School Center for Biomedical Informatics for 10 years. Kate has a Bachelor degree of Science with honors from Cornell University and also a law degree from NYU School of Law. Wow, we have two fields then. Wow, very impressive. So I think we'll go to the presentation. I believe it's like 55 minutes in total. So perhaps 40 minutes for your presentation and 15 minutes for question, but we can adjust it later.
Yeah, yeah, I'll do my best. Thank you very much. Should I share my screen now?
Yes, please.
Okay, let me do that. All right, so share the screen. Okay, great. All right.
Yes,
okay,
I can see your screen. Yes, it's good.
Great. Well, thank you very much. So now you know who I am. I can't see any of you, but I am honored to be here at the AI Summit for Indonesia. I was thinking, on a personal note, my first and only trip to Indonesia was in 1999 for my honeymoon. And so this is only a virtual visit, but it's nice to be back nonetheless. And I look forward to visiting again as soon as the world is back open. So again, now the goal today, my goal today, and of course it's a privilege to follow such esteemed speakers like Professor Yann from Facebook and others. My goal today is to talk about how NVIDIA is helping the world solve the most complex problems and level the playing field by democratizing access to the infrastructure that makes AI possible. There's a lot of different themes and narratives in there that we need to dive into and unpack. So I will do my best to cover them all in the time that we have and try not to fire hose you too much with information. But let's get to it. So I am not an astrophysicist, nor am I a cosmologist. I've never met Stephen Hawking, but I did have the privilege of meeting Carl Sagan when I was a student at Cornell back in the early 90s. I attended an open lecture by Dr. Sagan, who is a renowned planetary scientist. And one of the things that fascinated me, and Carl Sagan sort of inspired me to think about, was just the sheer scale of the field of the science that he studied and others like him. That the universe is unimaginably large, right? Like distance, for example. When we measure distance, it's not just in years, but light years. And just so you know, because if you don't think or study this, you might not have this at the front of your head, but a single light year equals 6 trillion miles. Okay, just to give you a sense of the scale, right? That's 6 followed by 12 zeros. Okay, so we have all of these amazing optical and radio telescopes pointed at the heavens, and scientists can see further and further into deep space than ever before. And actually, AI is increasingly playing a role in that. One of the reasons they do this, one of the reasons they look further and further is to understand how the universe began, right? To unravel the mysteries of the universe. So one mystery is how did the universe begin, and the other mystery is how may it end? How's the universe going to finally come to an end? And there's different scenarios. One of the scenarios is called the Big Rip, which you can just imagine in your head what that is. Another is called the Big Crunch. That's not too hard to imagine. And then there's one option that I find the most awful, which is the cosmic death bubble, although I find it to be the coolest sounding one. That's why I kind of featured it on my slide here. I mean, imagine this giant light speed bubble that just destroys everything in the universe, right? Now, the scientists think this is a very, very unlikely scenario, so no need for concern. And even if it was possible, it wouldn't happen for billions and billions of years from now. But the main point is that there is no technology that can actually foresee this. So you might as well not worry about it. We can't predict a cosmic death bubble. And so we might as well just move on. But what technology can do, what is true, is that technology enables us to see and shape the future. This is true. We may not be able to predict the rip or the big crunch or cosmic death bubble, but we can see and shape the future. One of the ways that technology allows us to do this is we can look deeper into our past. We can see beyond the limitations of human biology. We can see things that are otherwise invisible to us. We can do mathematics in a single minute that should take multiple lifetimes. That's what this technology can do. For example, and here's one very real example. You're working with NASA and the Frontier Development Lab. We've been able to see past the visible light spectrum to really actually see the dark side of the moon for the first time in human history, which is actually more than just a technology, a scientific achievement. It's enabling us to now plan a permanent moon base, which will be an important launching point for an eventual mission to Mars. So, there's many practical technology applications there. So but one of the questions you're probably wondering right now is why NVIDIA why is an executive from NVIDIA, widely known as a gaming company, speaking about artificial intelligence? I mean, what possible credibility could we have on the topic? So let's explain, because it's really quite an interesting corporate history. This is our CEO and founder, Jensen Huang. And nearly 3 decades ago, Jensen and his other co-founders conceived of a new kind of processor called the GPU, or graphics processing unit. Their goal was very simple. They sought to improve the visual experience for gamers. And by reinventing graphics, they helped launch the modern era of gaming. So this is about 30 years ago. And that is on now. I wasn't there at the time, but as I understand it, maybe the first or second generation of this chip wasn't a huge commercial success. This one, released in 2000, which you see on the screen, this was the first real successful consumer GPU. And what they knew in their heart is that great performance matters, because if you can improve the performance of the machines, the infrastructure underneath the gaming, then you can improve the gaming experience and you can really transform the industry. And today, 70% of the world's gamers get lost in synthetic worlds like Minecraft and Fortnite, enabled by NVIDIA and its technology. And we're very proud of this heritage, and we will continue to invest in gaming. It's the world's most successful sport, actually. More people game online than watch all of the spectator sports combined. So this is a great industry. But over time, our mission has evolved. And today, the same stack, the same accelerated computing platform, which I'm going to go into much more detail later, but the same stack of hardware and software that revolutionized the consumer and gaming industry now powers artificial intelligence from the cloud to the edge. So yes, it's still inside gaming towers, still inside gaming laptops, still being used by lots of teenagers around the world and young men and women that enjoy gaming. But that same technology now can also be found inside the leading national research institutes. It's inside major universities. It's across all of the public cloud providers. It's at the back of retail stores. It's on oil rigs. It's in the front room of hospital clinics. It's powering national or sovereign clouds. And it's also inside smart machines of all kinds: cars, robots, drones, satellites. So I talked earlier about the incredible scale of the universe, right? Just to set the stage, just to kind of get the wheels moving, so you can grasp and have some context for grasping the incredible scale of computing necessary to make AI possible. Now, most people in the normal lives do not encounter or think about supercomputers or AI supercomputers. But these are among the most complex machines ever built by man. And they perform calculations at speeds and in volumes that are not only mind-bending, not unlike the scale of measuring distances in the universe. Measuring the scale of compute is in the quadrillions, billions times billions, right? A similar type of scale. That's why I think it's an interesting metaphor. These machines, they make it possible to emulate human-like cognitive functions, like understanding natural language, even composing original pieces of music. And the professor, the previous speaker, certainly went into a lot of detail on these fronts. So but beyond modeling the universe, there's a lot more practical applications, right? Like predicting climate change and forecasting weather, right? Things that really do affect our lives. So even if we don't see these machines, we're not familiar with this technology, it's having a direct effect on our lives every day. But in order to really understand how NVIDIA is innovating in a way that democratizes access to AI infrastructure and why that's so important to Indonesia and the world, first I need to go back as well. We're not going to go back to the beginning of time, so we're done with the analogies to the cosmos, but let's go back a decade or so. Let's just get a little bit more knowledge. Look at the timeline of recent innovation around supercomputing, just so you have an appreciation for where we are now, right? So this is the Roadrunner. IBM built this system. This is a very, very important system. Now, I don't know where you were in 2007, but you probably, unless you're an HPC nerd or an AI expert, or you just live in this world, you probably missed this headline. And I'm not sure back in 2007 this would have made the front page of the New York Times like it would today. But in 2007, the Roadrunner system went live. And this was very important. This is the machine that broke the 1 petaflop sound barrier. I mean, this is significant because this entered a new age of high performance computing. Now, it took several years to plan this machine, right? 4 or 5 years to design, engineer, and plan this machine. It also cost over $100 million. So keep that in mind, right? It cost, but let's just use 100 million just to keep it simple. So it cost about 100 million to generate 1 petaflop of power. Now that's 1 quadrillion calculations of a specific kind every second. It's, again, like measuring the universe, numbers that are just mind-bending, right? The reason why this is important, because let's see, is when you keep that in your mind, 100 million for 1 petaflop. Now let's, and you can see the image on the screen, hundreds and hundreds of server cabinets, thousands of individual servers, tens of thousands of CPUs, right? And GPUs to get to this machine. But now let's jump ahead. This is the Titan. Titan was a beast, but actually smaller. Titan was 30% smaller, in fact. And it cost about the same, I think a little bit less than the Roadrunner. But Titan was 17 times more powerful. So about the same cost, a little bit less, 30% less space, significantly less energy consumption, and 17 times the power. So that's a pretty good jump in performance. Now let's go to Summit. Summit was a breakthrough. Summit was relatively recent, 2018, just a couple of years ago. This was the first supercomputer designed to be an AI supercomputer. It had thousands and thousands of NVIDIA GPUs optimized for AI workloads. This machine cost 200 million, but it delivered 200 petaflops of power, right? So just think of the mathematics there. Just about a decade earlier, it was 100 million for a single petaflop. 10 years later, it's 1 million for a petaflop. That is 100 times the power for the same cost. So now you have this $200 million machine, 10 times faster than the Titan, hundreds of times faster than the Roadrunner, and significantly less expensive per petaflop, right? Very powerful machine, still today operating, very, very important machine in the United States. Now, let's go 2 years after that to today, this summer, in fact. This is Selene. Selene sits at NVIDIA's headquarters. Selene is the fastest industrial AI supercomputer in the United States. It ranks 7th or possibly 6th in the latest rankings, I'm not sure, in the world for power. It's also the 2nd most sustainable, most power efficient. It delivers 1 exaflop. 1 exaflop is 1,000 petaflops. And it costs less than the Titan did just 6 years ago. So imagine that. 1,000 petaflops costing less than 100 million, when just in 2007, it was 100 million for a single petaflop. So this, I want to give you just this, again, a sense of the scale of power. And actually, I read that it has been argued that the human brain is essentially has 1 exaflop of power. So potentially, a machine of this scale and others like it have roughly the same compute power of the human brain. Now, of course, there's a big difference because the human brain works on the equivalent to about 20 watts, basically a light bulb. These machines are a little bit more energy hungry, right? So we can't come close to matching the power efficiency of the human brain. The other thing that's really significant about this machine, that's very, very important, it's not just about the cost or the efficiency or the speed. Those are all very important, but the scalability and deployability of the machines has also dramatically changed. What used to take years, remember Roadrunner, took years to plan, design, procure, install, configure, and operationalize. Years, right? And then you add to that the cost, right? I mean, if you think of the cost back then, it was 100 million for 1 petaflop, that meant a 5 petaflop machine might have cost 500 million, or a 10 petaflop machine might have cost $1 billion, right? So these machines were out of reach for the vast majority of countries in the world. They were out of reach for the vast majority of universities. They were out of reach for the vast majority of businesses and enterprises that needed them to drive their businesses forward. So the economics have changed, so has the reachability, the consumability, the access to the machines. Now, some of that has changed because of the public cloud. And we are grateful to the public cloud for blasting through so many barriers to the adoption of technology, including artificial intelligence. And then some of this technology is residing elsewhere. So we're going to get into that. But imagine where we'll be in another 10 years and how the arc of innovation in science and business will be impacted. Now, it's easy to fixate on these big computers in data centers, but it's important to remember that the topology of AI infrastructure is wider than just this. And so I have a slide on that. So when you think about AI infrastructure, it's distributed from the cloud to the edge. As I was saying, you've got the cloud. Of course, there's more than one kind of cloud. There's the public cloud, and then there's private clouds, including sovereign or national clouds. So these are different ways to consume this technology. You also have data centers that are owned or operated by governments and by companies and universities and aren't available to the public for a variety of reasons. And then you've got AI compute that also sits not in the cloud, not in a data center, but it sits at the edge, again, in these machines, right? Or in these locations. It could be an intersection for traffic. It could be in a building for a smart building. It could be in a satellite so that you can have a smart satellite. Obviously, it can be in a variety of other kinds of machines. But this is important because when you're thinking about, Indonesia is moving from talking about AI strategy to implementing AI programs. It has to focus on infrastructure that needs to support all these ambitions. And it's key to understand that AI compute doesn't just sit in a data center. So let's give some examples, right? So AI compute is this specialized stack of hardware and software that can be harnessed in different ways. For example, you could be deploying a delivery robot, right? I mean, that's coming. I mean, it's here. You just got to walk around San Francisco and you'll see. My son recently went to visit a college in Washington, D.C. And the robots are just zipping right along by him, bringing food to other hungry college kids. So these machines, these autonomous on-demand urban delivery machines, one of thousands of different versions of the different kinds of smart machines, right, that need this kind of technology. Now, of course, you can't pack a Titan or a Summit or a Selene into that, but you don't need to. That serves a different purpose. Now, maybe instead of a robot, you might have something a little bit bigger, like a car. NVIDIA very proudly signed a very exciting deal just 2 months ago, I think, with Mercedes. And the deal is to provide the complete infrastructure to create a software-defined vehicle of the future, to really enable the future of a passenger and driving experience, both the actual entertainment experience as well as the autonomous experience and all the technology related to that. And to make that happen, you have to pack a lot of technology into that car, both the sensors, the processors, and the software. Now, these are all edge devices. As I mentioned earlier, you're not going to put a huge data center computer in there. So what goes inside there? Something like this. This is the Jetson family of supercomputers, which are the smaller form factor that goes inside these edge devices, right? I mean, these are effectively supercomputers. They perform mean, they operate at a scale that is far, far beyond a traditional classic computing model, but they have a role to play, right? They take the models that have been designed on the larger computers, then you shrink them down into what we call the inference model. And that inference model runs at the edge, right? And it's connected back to that supercomputer. And that's what this looks like. And that's one of the interesting things, because the intelligence of these machines, or the intelligence of smart medical devices, or smart buildings, or smart cars, or whatever it's going to be, whatever is going to be smart, that intelligence starts with a model that has been trained back at HQ, or perhaps in the public cloud. But it is that sort of end-to-end hardware, software suite of technology that enables you to train robots to be robots, frankly, and to train in a hyper-realistic synthetic world where they can make mistakes, they can have accidents, millions and millions of times over and over and over again until they learn how to do it right. And just like the Matrix, they can be downloaded from this hyper-realistic synthetic world into the physical machine and then have sort of a relationship with that supercomputer back and forth. So the car is going to continue to drive around the world. You know, it's going to continue to operate in the real physical world, but it's going to share knowledge back with the supercomputer in that synthetic world. And that's the kind of, and it's that kind of relationship between, across that distributed architecture between the cloud, the data center, and the edge. That's really what's going to make possible this incredible future that we're interested in. And and of course there's a fabric between them, right? You have 5G that connects you to the edge, right? And you have data centers and all that sophistication. So, you know, there's a lot of moving parts here, right? So I wanted to really kind of make it clear about also how our heritage in gaming really ties to our future in artificial intelligence, because the same technology, the same skills, the same resources, even the same partnership ecosystems that we used to create this incredible business around gaming and to, again, enable these synthetic worlds where people get lost for playing, we have applied that to the real world. The same laws of physics apply, the same visualization, the same sort of aspiration to achieve hyperrealism. And so leveraging that toolkit, leveraging that capability across all of these different industries, which we now do in the auto sector and healthcare and retail and in manufacturing, right? It's all of these are just sort of new ways to repurpose and build on this incredible legacy that continues to this day on gaming. It's really quite interesting. One would never know that all these teenagers around the world who are playing games, the role that they play, the role that they're actually, the way that they're contributing to the future arc of innovation around artificial intelligence. I guarantee you that they don't realize how they're connected to all this, but it's really quite interesting. Now, this is a lot of information, but I really wanted to make sure you had some exposure to the idea that AI infrastructure is this spectrum of very specialized technology. It combines hardware and software, and then it runs from the cloud to the edge, right? I mean, those are some of the key principles. So I've now presented on what is AI infrastructure from this kind of strategic view, right? And kind of how it's making an impact in different ways. But let's pivot now, and let's talk more about why it matters. I mean, why are we talking about this at all in the context of this incredible summit at this time in history? Let's talk about that. So there is a global AI policy imperative. It's incredible. Since before June 2017, actually, there wasn't a country in the world that had an AI strategy. Not one. Today, 60 or 70 countries have published a national AI strategy, and it's typically championed by the head of state. Now, that happened very, very fast, very fast. And I don't think that there's another example of that. I mean, you know, over the last 20 odd years, you know, as technology has transformed our lives, whether it's, you know, business technology like ERP software, or it's the Internet of Things, or just the, you know, the internet itself, you know, things took years, and usually the industry, right? The technology innovations that drove business were years ahead of policy. The policy environment and the just grasping the implications of the technology, and then moving and then translating that knowledge into regulation and or other kinds of policies that could even provide stimulus and incentives around that technology, lagged by many, many years. But that's not true with AI. What's interesting about AI is it has inspired an altogether different response. There is this incredible policy imperative on a global scale. And also, as these plans have emerged, there's kind of a shared recipe across them. And I created this one slide to capture that shared recipe. You know, often you have this national sponsorship almost exclusively. I'm not sure there's any country where you don't have that. So these are very high profile, often head of state driven type of initiatives. There's usually a lot of stakeholder engagement, open public consultation periods, working groups and working committees. I've worked with many, many countries on this, and again, they take slightly different approaches, but by and large, very similar, very extensive engagement, both in the academic community, in the government community, in the business community. Perhaps if there's one area where there might be a weak spot, and it's not intentional, but reflecting on it, the average citizen probably wasn't involved as directly in the development of these plans, but I'm not sure there's a real practical way to do that. So it's something to think about going forward. But what has been part of many of the plans, and is a very clear theme, is the focus on citizen benefit. That is an accountability to citizens, that this is not just an academic exercise or just about writing a plan. It's about creating value for the country. And that is very clear. That's reflected in many of the plans. So usually there's 4 components to these plans, right? Here's the recipe. There's a strategy. And again, 60, 70 countries have published a strategy. Some countries like the UAE have even come back and published version 2 of their strategy. And I think that's very smart. I mean, a strategy needs to be a living, breathing document. It cannot, you can have a charter that's very, very high level, but if the strategy is going to have value, it needs to continuously be refreshed, along with the very dynamic field of artificial intelligence, and of course the broader environment of that country and the things that are going on. So strategies are plentiful. We have those. Then you have next to that, we'll call them policy and laws. And I think that's also a very robust narrative there. You have a lot of activity on both a national and a global level. The United Nations, the World Economic Forum, the OECD, many, many organizations getting involved, many universities forming institutes, and then within countries, there's certainly a very robust debate on how to regulate, what to regulate, how to protect citizens, how to protect human rights, right? Because AI is there's a double-edged sword. This is a dual-use technology, not unlike nuclear technology. There's incredible use cases that could transform society and address some of the most incredible challenges of humanity, but there's also known risks, and there's applications and ways to abuse this technology and to apply it in ways that would not be beneficial to society. So lots of conversation, lots of good dialogue, and lots of innovation, and particularly in Europe around trustworthy AI and AI ethics and so forth. And I think NVIDIA and many of the leaders in this industry support that dialogue and want to participate and obviously let that run its natural course. Now, that's on the left side of the equation. On the right side, it gets a bit more tactical, a little bit more tangible. That is the ecosystem and the infrastructure. And really, they're both important. Now, NVIDIA, our commercial business is on the infrastructure side, right? But we recognize, as do most of the industry, that if you don't have the right talent and capabilities and other elements of an ecosystem around that infrastructure, then it's not very effective. You really had to build, and an ecosystem is a simple word, but I'm referring to layers and layers, entrepreneurs and startups, students, graduate students and professors, investors, both foreign and domestic. You've got established industry. This is the ecosystem, and the most successful super hubs in the world, and both the cities and countries that are getting the most value from their strategy, from their infrastructure, they're spending a lot of time and energy in investing and growing that ecosystem in different ways. Many different ways to do that. There isn't a single formula, but you either have a genuine commitment or you don't. And so there's the ecosystem, and then there's the infrastructure. Now, the infrastructure I've spent the last 28 minutes talking about to some degree, but that of course you can have a great plan, you can have robust policy dialogue and emerging policies on that front, you can have a robust and thriving ecosystem. But if you do not have world-class AI infrastructure, then none of those ideas will actually come to fruition. You need to have, that is obviously an essential part of the recipe. And ultimately, why do this at all, right? Within any given country, all of these things are not academic. These things matter, and they matter because they connect to economic growth and public health and safe cities and national security, engaged citizens, right? This technology has very real implications for the world. So let's talk about Indonesia. You know, transforming Indonesia into a fourth industrial revolution economy has become a focus for your government over the past few years. And recently, Indonesia published its national AI strategy, as I've represented here on the screen. You know, I think it's a fantastic plan, and it supports, you know, 5 national priorities, which are clearly laid out here. And I think the government has articulated a plan that reflects the real strengths of the country. I've studied and worked on and written some of the plans around the world, and I was looking at Indonesia's plan and trying to identify, you know, what is notable. And so I just want to point out 3 things about the plan that really stand out for me. Number 1, I believe it is the only national AI plan that prioritizes food security. I haven't seen it. I mean, it's possible I missed it, but I'm pretty sure it is the only one in the world that prioritizes food security. And I think that's very interesting, and that's very cool. There's a very ambitious plan to enable 98 smart cities and 416 smart districts. Now, that by itself is not unique, the smart cities, but the specific number is quite ambitious and suggests, you know, a lot of planning and thought, right? That I don't believe that was pulled out of a hat. And finally, it places a heavy focus, as it says here on number 2, bureaucratic reform, right? The digitization of the government, recognizing the need to leapfrog over the current bureaucracy to create a new AI-enabled citizen experience. This is very, very important. And I think it's great that Indonesia has brought this out. This is a well-constructed plan. And of course, it's about more than just adopting new technology. It is about the future of the country. So let me share, you know, a perspective on why I think that plan is so important and what you do with it is so important. For the last 100 years, I don't know, more or less, 75, the basic infrastructure on which countries were created is concrete. Concrete is still very, very important. We still need to build roads. We still need to build bridges. We still use concrete. I laid some concrete, actually, at the end of my driveway just the other day. Concrete's not going anywhere. In fact, if anything, concrete's getting smart because there's going to be lots of sensors inside concrete. But concrete is not the only infrastructure that matters. AI infrastructure is the new axis for global competition. Going forward in the calculus of national economies in terms of driving GDP, there will be a more direct relationship to that country's ability to translate data into value than there will be in just concrete. Now, historically, supercomputers and artificial intelligence have been an engine for discovery, scientific discovery, and that has not changed. That's still true. They've been time machines for scientists, right? Able to take what could take 1,000 years and condense it into a year, or 12 months and do it into 12 hours. Actually, let me give you a great example. This is a real example. So I mentioned the Summit computer earlier, right? So the Summit computer, like many of the world's AI supercomputers, have been focused on the COVID-19 crisis, right? Trying to discover, you know, and accelerate the identification of vaccines and treatments that will help us get through this very difficult time in history. Typically, under normal conditions, without access to a supercomputer powered by GPUs like the Summit, researchers, clinical and life science researchers would need 12 months to look at 1 billion compounds. That would be the pace of discovery. It would take a year to go through 1 billion molecular targets and to test them and to identify which might be a possible candidate for further development. Well, using the Summit computer and using our technology, that 12 months has been condensed into 12 hours. So imagine, what should take a year can now take a half a day. That is more than fast. That is a time machine, right? That opens up completely new possibilities for vaccine development. So that's incredible stuff. But now that same machine, that same architecture is now an engine for economic growth. It's an engine for industrial innovation, for customer service innovation, for startups. It helps governments make their agencies more accessible to their citizens. It can help detect disease and other kinds of threats to the public health, including food security. It can help plan and manage increasingly condensed urban environments, right? So this infrastructure is not just about science and awards and researchers. That's still true. But now there's 2 or 3 more layers to the value, to the policy case. And I think increasingly we're going to find out that these machines will be the new proxy for growth in many countries. So now, NVIDIA knows a thing or two about execution and growth. This is kind of a busy slide, so I'm going to cover most of it up. I just want to focus on the left side. Our innovation model should be a template for countries, and just demonstrates that it's important to innovate at many levels to achieve your goals. We take our hardware, which is the core of our company, but which, where we push the boundaries of manufacturing and engineering, right? And that's our GPUs and the whole systems that we design there. And then we put on top of that the software. Now, the software is not bound by the limits of physics. That's bound by the limits of human ingenuity. And we have thousands. In fact, we have more software engineers than we do hardware engineers at NVIDIA. And so software engineers all around the world working around the clock to continuously push out updates and to create innovations that enable the hardware to operate at ever faster speeds and levels of performance. Then on top of that, we take the open source frameworks created by millions of developers and we accelerate those. And then on top of that, you've got thousands, hundreds and thousands of software vendors and other kinds of partners, OEMs and VARs and consulting firms that have optimized and built solutions on top of our hardware and our software and the frameworks. So you've had 4 layers of multiplied value innovation. So what happens when you do that? Well, this is what happens. A few weeks ago, the Wall Street Journal declared that Moore's Law is no longer the trajectory of innovation on compute. That silicon chips that power AI are more than doubling every 2 years because of the innovations in both hardware and software as represented by NVIDIA. And you can see the curve there on the GPUs versus CPUs. So our model is now is not just helping us succeed. It's not just helping NVIDIA grow and achieve, good returns for our shareholders. It's directly impacting the pace of technology innovation in the world. So here's how it gets very, very real. Again, if you're an HPC nerd and you live in this world and you know a lot about these machines, and then you've heard of this, but many people haven't. And the top 500 is one of the few lists. It's one of the few standard metrics for measuring AI compute. And if you look at this list, what's really interesting is that less than 30 countries are on it. And even there, the vast majority of these machines of the fastest computers in the world sit in 2 countries, China and the United States. So what does that mean? That means these innovations are available. This technology exists in the world, but it's not evenly distributed. And that makes a huge impact on the future of the geopolitical balance, on countries' ability to achieve their national AI plans, and all of these things we talked about. So our contribution, and what we're quite proud of, is technology. I gave you this example earlier, right? Let's go back. 2007, 1 petaflop, $100 million. Today, an NVIDIA DGX AI server, which is about 263 pounds, I think, a single server, can deliver 5 petaflops of power for $200,000. In 2007 terms, that would be 500 million. So what would cost 500 million just 13 years ago now costs 200,000. Now you stack 5 or 6 of those into a rack like you see on the screen, and it replaces an entire data center of technology. 650 servers, 25 racks, consuming incredible amounts of technology, taking up a lot of space, needing a lot of overhead. Only available to certain countries, only available to the biggest companies in the world. Now, you democratize that infrastructure, and you put it into a rack that takes up 1/25th the space, 1/20th the energy, and 1/10th the cost. This is what democratized AI infrastructure looks like. And so it does more than create a faster computer at lower cost. It completely changes the economics of AI. So to come full circle, to wrap it up, NVIDIA, we're quite proud of our role in enabling all nations to become AI nations and helping, and whether that technology is being consumed in the cloud, being consumed in a data center, or it's being pushed out to the edge. Enabling countries around the world, small countries, large countries around the world, to take advantage of this technology to advance their economic agenda and their national goals is something that we take pride in. And that's why we appreciate this opportunity to speak at this conference. So with that, I'm going to stop sharing my screen because I am concluded. Thank you very much for listening.
Thank you very much, Kate. Okay, big applause. Thank you very much. I'm very amazed, 12 months into 12 hours, very cost efficient. And then thank you very much for your input for the Indonesia and national strategy. Sure. It is very good. I mean, now we're going to go to the question and answer. We have several questions from the audience, so we'll read it for you. The first one, infrastructure, platform, and development of AI cannot be separated. In your opinion, based on your experience, which one is the best solution between making a big centralized data infrastructure or distributed data infrastructure?
Yeah. I don't know that there's a simple answer to that question. You really need to understand that AI infrastructure. So here's one of the common misunderstandings, that AI is not the same as IT, right? IT, the sort of classic computing and storage infrastructure at this point, has been so well standardized and perfected. Again, in large part because of the cloud, the public cloud companies and the incredible efficiency that they bring to that model, that IT can be consumed at scale in a very efficient way, like a utility, quite frankly. We are on a journey with AI and AI compute infrastructure to get there. We want to get there. We want the world to have access to that same sort of highly accessible, highly consumable AI compute in the cloud. And we're getting there. I mean, the public clouds have a lot of NVIDIA technology in them, so you can consume the technology there. But depending on the specific problem you're solving, the economics, the security, or just there are other implications. Sometimes it makes more sense to have a complementary domestic infrastructure, and sometimes that infrastructure should be centralized, and there's value to having that as a cloud that's tapped into. And there's other times where it makes much more sense to put it at the edge. For example, certainly when you're dealing with a large number of sites and locations. So let me give you one example. We recently signed a deal with the National Research Organization in Ecuador, CEDIA, and working with a large telecom provider as well. They are launching a national AI research cloud, basically, to serve the 50 or 60 universities in Ecuador. And it makes much more sense to do it that way, to have a central data center, with a supercomputer that then pushes out this private research cloud. Versus each one of those universities having their own supercomputer. In that example, the distribution would make sense. But on the other hand, many of the world's largest supercomputers sit at universities, and often universities want to have them because it brings prestige and funding, and it enables them to attract scientists. So, it's not always just about efficiency and cost. There's other reasons to have a machine, within your roof, frankly. And so it's hard to answer that's a great question. It's hard to give one simple answer.
Okay. Actually, your example of Ecuador, the second question is related with that. The second question is that, is there any similar use case with Indonesia's condition that you have experienced before in order to develop best AI infrastructure design? So what would you suggest to us?
Yeah. Well, one of the benefits of being in my role here at this incredible company is that we work with governments all across the world, and of all sizes. In fact, right now, the smallest country probably should mention them, but I'm working with a very small island nation with less than 1 million residents. It's a very small country, and of course also working with countries as big as India. With over 1 billion people and a very large landmass, right? So countries of all sizes, and I don't see. They're not all taking the same approach, quite frankly. There's there's a political reality in those countries. There's an economic reality. There's a bureaucratic reality. There's the distribution of power and funding and the way that happens in each country. In some countries, it's concentrated more at the federal level. In other countries, the power and the funding goes more down to the states. So, Indonesia is one of the largest economies in the world, right? And an enormous, huge population, large economy, but it's also very, very distributed and many, many islands and physical separated locations. So it might make sense to have a blend, where you might need to put some infrastructure, in various locations that makes it easy to access, even in the event of look, let's not forget, I think if this year has taught us anything, it's that these black swan events happen, right? These incredible events happen that challenge our infrastructure, right? So whether it's a tsunami or a pandemic or whatever, clearly, sometimes you need to plan ahead. So from a continuity perspective, I would think a country as large and distributed as Indonesia might need a combination of both.
Okay, I understand. Yeah. Thank you. I mean, I think we have another. Okay, I have one question. Okay. Sure. I'm a university lecturer, so I really into the talent development. So I would like to ask your opinion about the readiness of AI talent in Indonesia to maximize the usage of the AI infrastructure.
Yeah, this is so important. We have noticed there are some countries where their ambition and their vision is fantastic, and they're investing in areas, but if you don't have the people to look, this is not just about technology. You must have the talent and the people, but it's a lot easier to buy a supercomputer than it is to find AI talent. I mean, it just is. In fact, if you were to send us a purchase order today, within a month or two, we would be delivering that machine, to your data center. But whether you had, the people to take advantage of that in the ecosystem, that takes years to cultivate. And I think countries are having sort of a reconciliation with that reality. Some countries just don't have enough data scientists and other of those skill sets. So I think countries clearly recognize that. A heavy emphasis, not just on training people today, but primary education, secondary education. You have to think about a generational change. You have to weave AI and data science as early as possible into the education. It's not good enough to just offer upskilling for current professionals. That's important, certainly in terms of job displacement, but that won't solve the problem. So I think you need to take a very holistic approach, K through 12, secondary, graduate, and then more advanced training, and you need to attack it at each level so that over the next decade you can position your country to address what will be a critical shortage of talent if it's not addressed.
You're right. Thank you. It should be a holistic approach. Actually, that one also written in our AI national strategy. Thank you very much, guys. It's very interesting. I'm very impressed. I got a lot of new knowledge now. So next,
Thank you, it was really, motivated speech that you're giving us all in this AI, Artificial Intelligence Summit, the first ever. And I think Ibu Ayu have moderated this session very nicely. And thank you for all your inputs, your comments on our national strategy. We're certainly working with NVIDIA toward many use cases that we are developing currently, and hope to always collaborate and synergize our effort in developing our national strategy on AI. Thank you so much.
Thank you very much. My privilege. Thank you.
Thank you, Pak Hamam.
Yeah, thank you, Bu Ayu.
Yeah, we're going to close the session, but I believe there is another photo session. Kit, we have a photo session. Perhaps Barara will lead the session. Thank you. Thank you again, all.
Thank you.
Yeah. Okay, Keith, would you please stay a little bit longer, Keith? Yeah, we would like to take a photo now.
Okay.
Okay. Everybody's ready? Okay, I count 1, 2, 3. Okay, thank you very much, Keith. It's midnight already there.
No, it's only 9 p.m. here. We're fine.
Oh, yeah, 9 p.m. Okay. Thank you so much, Keith. And also Ibu Anu.
Thank you very much.
Thank you again.
Thank you.
See you soon.
Bye. Baik, terima kasih Ibu Ayu Purwarianti yang sudah memandu tadi ya sebagai moderator kita pada Keynote Sessions yang keempat ya. Teknoprint tidak terasa sudah 4 session kita untuk hari ini. Dan nanti masih ada 5 sesi lagi ya. Nah, untuk 5 sesi nanti setelah kita break, jangan lupa ya harus stay tune Teknoprint karena kita akan ngobrol bersama Prof Toshio Fukuda, President of IEEE. Kemudian juga nanti sesi yang ke-6 ada Karina Cho, the Global Policy Lead for Emerging Technologies Google ya, temanya Emerging Technologies with Google Cloud. Kemudian juga untuk yang ke-7 nanti ada Anna Sawyer ya dari Deloitte, kemudian Vicky Setiono dari Microsoft, dan juga terakhir nanti akan ngobrol-ngobrol dengan saya ada Binma, Principal Engineer Alibaba Cloud Damo Academy of Singapore. Ya, kita akan break dulu ya Teknoprint, jangan kemana-mana dan Anda tetap bisa mengikuti ya Virtual Expo ini. Ada gamesnya, jadi ada platform games ketika Anda sedang menunggu di lobby Virtual Expo, Anda bisa mengikuti games dan ada kuis juga yang bisa diikuti oleh Teknoprint ya. Jangan lupa make sure harus follow dulu Instagram @stranas.ai ya, nanti di sana akan disebutkan kuisnya, ketentuannya seperti apa. Jangan kemana-mana, kita akan kembali setelah break jam 1, kita kembali Teknoprint. Selamat siang.